Hello there, and welcome to Science for Sleep, a place where reminders, schedules, and sharp edges can wait a little while, and where curiosity is allowed to slow its breathing. Wherever you happen to be right now, whether the day is ending or just beginning, it's good to have you here. You don't need to understand everything that's said. You don't need to remember details or hold on to facts. This is science offered gently, at a pace meant to relax the mind rather than challenge it. You're free to simply listen and let the ideas pass by, one at a time. Tonight we're turning our attention toward a single star, not one that dominates the night sky, not one that has inspired ancient myths or guided sailors across oceans. Instead, we're focusing on a quiet, nearby star that most people have never seen with their own eyes, even though it's closer to us than any other star beyond the Sun. Its name is Proxima Centauri, and the question we'll slowly work our way toward is a simple one on the surface, yet surprisingly rich once you sit with it. How big is Proxima Centauri, really? Before we begin untangling that idea, it might be nice to pause for just a moment and check in with yourself. Where are you listening from right now? Are you at home or somewhere unfamiliar? Are you lying down or sitting upright or drifting somewhere in between? And what time is it for you in this moment? Late at night, early in the morning, or during that quiet part of the day when everything feels slightly slowed down? These details matter, not because they change the science, but because they ground this conversation in the reality of your own experience, which is always unfolding in time and space. If you find this kind of calm exploration soothing, or if slow science helps your thoughts settle, you're welcome to like the video or subscribe to the channel. It helps this gentle approach reach others who might appreciate a quieter way of learning. There's no urgency. You can simply stay where you are and listen. Now, let's begin easing into the topic itself. When people hear the name Proxima Centauri, it's often followed by a quick explanation. It's the closest star to our Sun. That single fact tends to carry a lot of weight. Closest implies important. Nearby implies large. After all, in everyday life, the things closest to us usually appear bigger than things far away. A nearby tree fills your vision more than a distant mountain. A plane overhead looks larger than a cloud on the horizon. Distance shapes perception. But space doesn't play by those same rules so neatly. Proxima Centauri is close, at least by cosmic standards. Light from that star takes a little over 4 years to reach Earth. That sounds like a long time, and by human standards it certainly is, but in astronomical terms it's barely a step outside our own neighbourhood. And yet, despite that closeness, Proxima Centauri cannot be seen without a telescope. It's faint, it blends into the background, it doesn't announce itself unless you know exactly where to look and have the right tools. That contrast between proximity and subtlety is one of the first clues that size in space works differently than size on Earth. When we ask how big a star is, we often imagine something like a photograph. We picture an object floating in darkness, with clear edges we can trace. But stars don't usually offer themselves up that way. They're distant, bright points of light, and their apparent size in the sky tells us almost nothing about their true physical dimensions. A small star nearby can appear brighter than a much larger star far away. A massive star can look like a pinprick if it's distant enough. So before we can talk about how big Proxima Centauri is, we need to gently loosen our everyday assumptions about size. On Earth, size is intuitive. You can walk around an object, you can touch it, you can compare it to your own body. Even very large things like mountains or oceans are still part of a scale we live inside of. Space removes that familiarity. The distances are too vast, the objects are too extreme, and our usual mental shortcuts stop working. Proxima Centauri belongs to a category of stars known as red dwarfs. These are the most common stars in our galaxy, making up roughly 3/4 of all stars in the Milky Way. Despite that abundance, they're often overlooked in casual astronomy discussions, partly because they're faint and partly because they don't resemble the bright yellow-white sun that defines our daily experience of starlight. Red dwarfs are smaller, cooler, and less massive than the Sun. They burn their fuel slowly, producing less light and heat. Proxima Centauri is a textbook example of this type of star. Its surface temperature is lower than the Sun's, giving it a reddish glow, and its overall energy output is tiny compared to what we receive from our own star. But small and faint do not mean insignificant. Even the smallest stars are enormous compared to anything we encounter on Earth. Proxima Centauri has a radius about 1/7 that of the Sun. That might sound unimpressive when expressed as a fraction, but it still means Proxima is more than 100,000 kilometers across. You could line up Earth several times from one side of the star to the other. It has gravity strong enough to hold onto planets, generate nuclear fusion, and remain stable for trillions of years. Already the idea of size starts to stretch in unfamiliar directions. Another complication comes from the fact that stars don't have solid surfaces in the way planets do. When we talk about the size of a star, we're usually referring to the distance from its centre to the point where its atmosphere becomes transparent enough that light can escape. That boundary is fuzzy. It's defined by physics, not by a hard edge. So measuring a star's size is not as straightforward as measuring the diameter of a rock or a building. Astronomers rely on indirect methods. They look at how bright a star is, how hot it is, how it behaves over time, and how it interacts with nearby objects. From these observations, they build models that tell us how large the star must be to produce what we see. These models are tested, refined, and compared against other stars we understand better. In the case of Proxima Centauri, decades of observation have given scientists a fairly clear picture. It is small for a star, compact, and dense. It contains only about 12% of the Sun's mass, packed into a much smaller volume. That density plays a role in everything from its internal structure to its long lifespan. And lifespan is another place where size becomes misleading. Large stars burn through their fuel quickly. Their cores are hotter, their fusion reactions more intense. They shine brilliantly, but they don't last long. In contrast, small stars like Proxima Centauri sip their fuel slowly. They can shine steadily for trillions of years, far longer than the current age of the universe. In that sense, Proxima's modest size is a kind of quiet strength. There's also something oddly fitting about beginning a long, unhurried discussion with a star that itself is unhurried. Proxima Centauri is in no rush. It has been shining for billions of years already, and it will continue to shine long after stars like our Sun have faded. Its scale encourages patience, both scientifically and mentally. Still, the question remains, how do we really grasp its size? One helpful approach is comparison, not to abstract numbers, but to something familiar. The Sun is our natural reference point. Everything in our solar system is shaped by it. Our sense of what a star is, what starlight feels like, and how stars behave is grounded in the Sun's presence. So when we compare Proxima Centauri to the Sun, we're not just comparing two stars, we're comparing the unfamiliar to the familiar. But even that comparison needs to be handled gently. The Sun feels enormous to us because it dominates our sky and our lives. Yet in the broader context of the galaxy, the Sun itself is an average star. It's not particularly large, nor particularly small. It sits comfortably in the middle of the stellar population. Proxima Centauri sits below that middle. It is smaller, dimmer, and cooler. But it is also more typical. If you were to randomly pick a star in the Milky Way, odds are it would resemble Proxima more than it would resemble the Sun. In that sense, Proxima Centauri is not an oddity. It's a representative. This idea quietly reframes the question of size. Instead of asking how Proxima compares to the Sun, we might also ask how the Sun compares to Proxima-like stars. Suddenly, our familiar star becomes the outlier, brighter and larger than most of its peers. That shift in perspective is one of the subtle gifts of astronomy. It reminds us that our point of view is always local, shaped by where we happen to be. What feels normal here is not necessarily normal everywhere. For now, though, it's enough to let the image settle. a small red star close by in cosmic terms, quietly burning its fuel. Not dramatic, not flashy, just steady, persistent, and vast beyond any human scale. When we talk about Proxima Centauri as our nearest stellar neighbour, it's tempting to imagine a kind of cosmic closeness that feels almost familiar, as if this star were hovering just beyond the edges of our solar system, quietly keeping us company. The phrase nearest neighbour carries a certain warmth to it. It suggests proximity, relationship, maybe even a sense of shared space. But in astronomy, even the nearest neighbours live at distances that challenge every instinct we have about closeness. To begin understanding Proxima Centauri, it helps to first settle into what near actually means on a galactic scale. Proxima Centauri is a little over 4 light-years away from Earth. A light-year is the distance light travels in 1 year, moving at nearly 300,000 kilometers per second. When you put that into numbers, 1 light-year is about 9.46 trillion kilometers. Multiply that by 4, and you end up with a distance so large that writing it out feels more symbolic than practical. It's not a distance meant to be travelled easily or imagined casually. It's a distance that exists more comfortably in equations and maps than in intuition. And yet, in the context of the Milky Way, that distance is remarkably small. Our galaxy is about 100,000 light-years across. Stars are scattered throughout it like grains of sand in an enormous desert. Many of them are hundreds or thousands of light-years away from us. Some are tens of thousands of light-years distant. Against that backdrop, Proxima Centauri is right next door. If the Milky Way were the size of a continent, Proxima Centauri would be in the same city. This is why astronomers pay such close attention to it. Proximity offers opportunity. The closer a star is, the easier it is to study. Its light is stronger by the time it reaches us. Its subtle movements can be tracked more precisely. Its effects on surrounding space are easier to detect. Proxima Centauri gives scientists a rare chance to examine a star that is not our Sun in unusually fine detail. But even before modern telescopes and measurements, Proxima Centauri's story was shaped by careful observation and patience. For much of human history, Proxima Centauri was completely unknown. It is too faint to be seen without optical aid, even though it resides in the same region of the sky as Alpha Centauri, one of the brightest star systems visible from Earth's southern hemisphere. Ancient observers could see Alpha Centauri A and B as a single bright point of light, but Proxima remained hidden, lost in the darkness. It wasn't until the early 20th century that Proxima Centauri was identified as a distinct star. In 1915, Scottish astronomer Robert Innes noticed a faint star near Alpha Centauri that appeared to share the same motion across the sky. This shared motion was a crucial clue. Stars that move together are often physically related, bound by gravity rather than simply aligned by chance. Over time, measurements confirmed that this faint red star was not only associated with Alpha Centauri, but was slightly closer to us than the brighter pair. That discovery reshaped our understanding of our local stellar neighbourhood. Suddenly, the closest star to the Sun was not a bright, sun-like object, but a dim red dwarf, quiet, small, easy to overlook. This detail alone hints at something important. The universe does not prioritise spectacle. The objects closest to us are not necessarily the ones that shine the brightest or draw the most attention. Sometimes the most significant discoveries are subtle, requiring careful measurement and a willingness to look past the obvious. Proxima Centauri is gravitationally bound to Alpha Centauri A and B, though it orbits them at a great distance. The trio forms a loose system, with Proxima following a long, slow path that may take hundreds of thousands of years to complete a single orbit. This means that while Proxima is part of the Alpha Centauri family, it lives far from the centre of activity, spending most of its time in relative isolation. This isolation has consequences. Proxima Centauri evolved somewhat independently from its brighter companions. Its small mass shaped its internal processes from the beginning. While Alpha Centauri A and B resemble the Sun in many ways, Proxima followed a different path, becoming a red dwarf early in its life and settling into a long, stable phase of slow fusion. Understanding Proxima as a neighbour also means understanding how stars move. Stars are not fixed points. They drift through space, each following its own orbit around the centre of the galaxy. Over long periods of time, neighbourhoods change. Stars pass closer or drift farther apart. Proxima Centauri will not always be our nearest stellar neighbour. Millions of years from now, another star may take its place. Millions of years before now, a different star may have been closer. This dynamic nature of stellar neighbourhoods adds a quiet layer of impermanence to the idea of proximity. Proxima is near now, but now in cosmic terms is a fleeting moment. Despite that, Proxima's current closeness has made it a focal point for both observation and imagination. Because it is nearby, scientists can measure its distance with high precision using a method called parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this tiny shift, astronomers can calculate distance with remarkable accuracy. Proxima Centauri was one of the first stars whose distance was measured this way, and it remains a benchmark for stellar measurements. Distance, however, is only the beginning. Once astronomers knew how far away Proxima Centauri was, they could begin determining other properties. Its brightness, when corrected for distance, revealed its true luminosity. Its colour revealed its surface temperature. Its motion revealed its mass. Each piece of information helped refine our picture of this nearby star. What emerged was a portrait of a star that is physically small, cool, and faint compared to the Sun, but also active in its own way. Proxima Centauri emits much less visible light than the Sun, but it produces a significant amount of energy in other forms, including ultraviolet and X-ray radiation, especially during flares. These outbursts can dramatically increase its brightness for short periods, reminding observers that even small stars can be volatile. This activity complicates the idea of Proxima as a calm neighbour. On one hand, it is steady and long-lived. On the other, it can be unpredictable. This duality is typical of red dwarfs. Their interiors are fully convective, meaning energy moves from the core to the surface through constant churning rather than layered flow. This contributes to magnetic activity, which in turn drives stellar flares. From a distance, Proxima Centauri appears unassuming. Up close, it is dynamic. Another reason Proxima Centauri captures so much attention is its planetary system. In 2016, astronomers announced the discovery of Proxima b, a planet roughly Earth-sized orbiting within the star's habitable zone. The habitable zone is the region around a star where temperatures could allow liquid water to exist on a planet's surface, assuming the right atmospheric conditions. The discovery of Proxima b transformed Proxima Centauri from a point of academic interest into a symbol of possibility. Suddenly, the nearest star was not just a reference object. It was a potential host for a world that might share some basic similarities with Earth. That possibility immediately raises new questions, many of them tied directly to Proxima's size. A small star has a small habitable zone. Planets must orbit very close to remain warm enough. That closeness exposes them to stellar activity, flares, and radiation. The star's size, mass, and behaviour all shape the environment of its planets in fundamental ways. So even when we talk about Proxima Centauri as a neighbour, we're not just talking about distance, we're talking about influence. The star's gravity governs its planets, its radiation shapes their atmospheres, its size determines how stable or hostile their conditions might be. It's also worth noting that Proxima Centauri challenges another quiet assumption. We often imagine that the stars closest to us would be similar to the Sun, simply because the Sun defines our experience of what a star is. But Proxima Centauri reminds us that the Sun is not the standard. It is one example among many. Our nearest stellar neighbour is fundamentally different from the star we orbit. This realization has broader implications. If red dwarfs like Proxima are the most common stars in the galaxy, and if many of them host planets, then a large fraction of potential planetary systems in the Milky Way may exist around stars very different from our own. Understanding Proxima is, in a sense, practice for understanding the majority of stars and worlds in our galaxy. As you sit with this idea, it may begin to feel less surprising that Proxima Centauri is small. Small stars are common. Large stars are rare. Bright stars attract attention, but faint ones do most of the work of quietly populating the galaxy. Meeting Proxima Centauri, then, is not like meeting a celebrity. It's more like meeting a representative, a nearby example of a vast population of stars that quietly shape the structure of the Milky Way. When we use the word big, it usually slips into conversation without much resistance. Big houses, big storms, big ideas. It's a word that feels intuitive, almost instinctive, shaped by daily experience and physical presence. Something is big because it takes up space around us, because it's hard to move, because it blocks our view or demands our attention. On Earth, bigness is tied closely to scale we can walk around, touch, and compare to our own bodies. But the moment we apply that same word to stars, especially to something like Proxima Centauri, the meaning begins to loosen. The familiar anchors fall away. We can't stand next to a star. We can't circle it with our eyes or feel its mass beneath our feet. Everything we know about stellar size comes through layers of interpretation, measurement, and comparison. So before we can reasonably ask how big Proxima Centauri is, we need to slow down and ask a more basic question. What do we actually mean when we say big in an astronomical context? One of the simplest meanings of big is physical size, diameter, radius, how wide something is from one side to the other. This is usually the first definition people reach for, and it's a reasonable starting point. For planets, physical size is relatively straightforward. They have solid surfaces or well-defined atmospheric boundaries. For stars, things are less tidy. A star doesn't have a hard surface in the way a planet does. Instead, it has layers of plasma that gradually thin out as you move away from the core. Astronomers define a star's size based on where its light escapes, a region known as the photosphere. This boundary is defined by physics, not by touch, and it already introduces a layer of abstraction. Even with that definition in place, physical size alone doesn't tell the whole story. Two stars can have similar diameters, but behave very differently. One might be massive and dense, another light and diffuse. One might burn fuel rapidly, the other slowly. So diameter gives us one piece of the picture, but not the full portrait. Another common meaning of big is mass. How much matter something contains. In many ways, mass is more fundamental than size. Mass determines gravity. Gravity shapes orbits, pulls material inward, and controls how a star evolves over time. A star's mass dictates the pressure in its core, which determines how quickly nuclear fusion occurs. That fusion rate sets the star's temperature, brightness, and lifespan. In astronomy, mass is often the most important single property of a star. Two stars with slightly different masses can have dramatically different lives. One might become a red giant and explode as a supernova. Another might quietly fade into a white dwarf. So when scientists talk about a star being big, they're often thinking primarily in terms of mass, even if that's not obvious in everyday language. Then there's brightness, which complicates things further. Brightness feels like size to the human brain. Brighter objects seem bigger, dimmer ones seem smaller. This instinct is deeply ingrained because on Earth, brightness often correlates with proximity and physical scale. A nearby fire looks larger than a distant one. A brightly lit building stands out more than a shadowed one. Stars break this association completely. A star can be physically enormous, but appear faint because it's far away. Another can be physically small but appear bright because it's close, or because it emits a lot of energy per unit area. Proxima Centauri is a perfect example of this confusion. It is close, but faint. Much fainter than many stars that are far more distant. If brightness were our only guide, we might assume Proxima is tiny in every sense. The reality is more nuanced. Energy output, or luminosity, is another way astronomers think about size. A star that produces a lot of energy feels big in its influence. It heats surrounding space, illuminates planets, and dominates its local environment. The sun's luminosity defines life on Earth. Even small changes in its energy output would have dramatic consequences for our planet. Proxima Centauri produces only a tiny fraction of the sun's luminosity, less than 1%. In visible light, it's even less. That low output is tied directly to its size and mass, but it also affects how we think about its role. A star that emits less energy feels quieter, more reserved, even if it is still enormous by human standards. There's also volume to consider. Volume scales quickly with radius. If you double a star's radius, its volume increases by 8 times. This means that relatively small changes in size can correspond to huge differences in how much space a star occupies. When we say a star is small, we may be underestimating just how much larger it still is than anything familiar. Density adds yet another layer. Density is mass divided by volume. Some stars are incredibly dense, packing large amounts of mass into relatively small spaces. Others are swollen and diffuse, with outer layers that are loosely held together by gravity. Red giants, for example, can be enormous in diameter, but relatively low in density. Red dwarfs like Proxima Centauri are comparatively compact. They pack their mass into a smaller volume, resulting in stronger surface gravity than you might expect from their size alone. So when we say big, do we mean wide, heavy, bright, influential, or long-lasting? In astronomy, all of these meanings coexist, and they don't always line up neatly. This complexity is why comparisons are so important. We rarely talk about stellar size in isolation. We talk about how one star compares to another. Proxima Centauri compared to the Sun compared to a red giant compared to a supergiant. Each comparison reveals different aspects of what big can mean. For Proxima Centauri, most comparisons begin with the Sun because it's our reference point. The Sun feels big to us because it dominates our sky and our lives. It contains more than 99% of the mass of the solar system. Its gravity holds planets, asteroids and comets in their orbits. Its energy drives weather, climate and biology. By these measures, the Sun is enormous. Yet in the broader population of stars, the Sun is average. It's not particularly massive, it's not particularly small, it sits comfortably near the middle of the distribution. Proxima Centauri sits well below that middle in terms of mass and size. But below average does not mean negligible. One way to make this more concrete is to think in terms of thresholds. There is a minimum mass required for a star to sustain hydrogen fusion in its core. Objects below that threshold are called brown dwarfs. They glow faintly from residual heat and limited fusion reactions, but they never fully ignite as stars. Proxima Centauri sits safely above this threshold. It is a true star. It fuses hydrogen steadily. It will continue doing so for trillions of years. So even though Proxima is small compared to the Sun, it is not barely a star. It is comfortably within the stellar category. Its size is sufficient to sustain long-term nuclear fusion. That alone gives its bigness a kind of legitimacy. Another useful angle is influence over time. Some objects are big because they do a lot quickly, others are big because they do a little, for a very long time. Massive stars dominate their surroundings while they live, but their lives are short. They burn fast, explode, and scatter heavy elements into space. Red dwarfs like Proxima Centauri contribute more quietly. They provide stable energy over enormous spans of time. They may host planets for trillions of years, far longer than Sun-like stars ever could. In that sense, Proxima's size grants it endurance. Its small mass leads to slow fusion. Slow fusion leads to longevity. Longevity leads to opportunity, especially for planetary systems that need time for complex processes to unfold. This brings us to another subtle meaning of big: importance. We often conflate size with importance, but the two don't always align. A small component can play a crucial role. In galaxies, the most massive stars are rare, but the most common stars, red dwarfs, collectively contribute a great deal to the galaxy's mass and structure. They shape the long-term evolution of the Milky Way simply by being so numerous and so persistent. Proxima Centauri, as an individual star, is not especially influential on a galactic scale, but as a representative of a vast class of stars it becomes important. Studying it helps astronomers understand red dwarfs in general. Understanding red dwarfs helps us understand the galaxy as a whole. So when we say big, perhaps we should also ask big in what context? Big compared to Earth, big compared to the Sun, big compared to the average star. Big in terms of physical size or big in terms of influence over time. Each of these frames produces different answer, and none of them are wrong. They simply highlight different aspects of the same object. This layered meaning is part of what makes astronomy both challenging and calming. Challenging, because it resists simple answers. Calming, because it encourages patience. You don't get to rush to a conclusion. You have to sit with the question and let it unfold. As we apply this to Proxima Centauri, the picture becomes clearer. It is physically small for a star with a radius much smaller than the Sun's. It is low in mass, containing only a fraction of the Sun's material. It is dim in visible light, producing far less energy. But it is dense, stable, and extraordinarily long-lived. It is close to us, making it accessible for study. It hosts at least one planet, making it relevant to questions about nearby worlds. So is Proxima Centauri big? Yes, in human terms, unimaginably so. Is it big compared to the Sun? No. Is it big compared to the smallest possible stars? Yes. Is it big in importance? In some ways, very much so. All of this suggests that asking how big Proxima Centauri is cannot be answered with a single number or comparison. It requires context. It requires a willingness to hold multiple meanings at once, and it requires us to be careful with language, especially words that feel simple but carry hidden complexity. With that groundwork in place, we're now better prepared to move forward. Instead of relying on vague impressions, we can start looking at concrete comparisons. Set beside our Sun, Proxima Centauri immediately changes character. What felt abstract a moment ago becomes concrete the instant we give the mind something familiar to hold on to. The Sun is not just another star to us. It is the reference point around which our instincts, our calendars, and our physical existence are built. Every sense we have of warmth, daylight, and seasonal rhythm traces back to it. So when we compare Proxima Centauri to the Sun, we are not just comparing two stellar objects. We are recalibrating our understanding of what a star can be. The Sun measures about 1.39 million kilometers across from one edge to the other. That number is already difficult to visualize, but it helps to remember that more than 100 Earths could fit side by side across its diameter. Its volume is so large that roughly 1.3 million Earths could fit inside it. These figures aren't trivia. They describe a gravitational anchor so dominant that it holds nearly the entire mass of the solar system within itself. Proxima Centauri, by contrast, has a radius of roughly 100,000 kilometers. In relative terms, it is about 14% the radius of the Sun. That difference may not sound dramatic at first, but volume scales with the cube of the radius. When you apply that scaling, the contrast becomes striking. Proxima's total volume is less than 1% of the Sun's. If the Sun were hollow, you could fit more than 1,000 Proxima Centauris inside it. This alone answers part of the question of size. Physically, Proxima Centauri is far smaller than our Sun. It occupies much less space. It presents a much smaller surface area from which energy can escape, and that reduced surface area has immediate consequences for how much light and heat it produces. The Sun's surface temperature is about 5,800 degrees Celsius. Proxima Centauri's surface temperature is closer to 3000 degrees Celsius. That difference shifts the star's output toward longer wavelengths of light. The Sun emits most of its energy in visible light, which is why daylight appears bright and white to our eyes. Proxima Centauri emits much of its energy in the infrared. To human vision, it appears dim and reddish. Luminosity brings the comparison into even sharper focus. The Sun outputs about 3.8 gigs 10^26 watts of power. Proxima Centauri produces roughly 0.15% of that. In visible light alone, it produces far less. If Proxima Centauri replaced the Sun at the centre of our solar system, Earth would freeze solid. Oceans would lock under ice. Even at the closest possible stable orbit, a planet would receive only a fraction of the warmth we currently enjoy. Yet this is not a failure on Proxima's part. It is simply the result of physics. Smaller mass leads to lower pressure in the core. Lower pressure slows nuclear fusion. Slower fusion produces less energy. The Sun's larger mass compresses its core more tightly, driving fusion at a faster rate and producing far more power. Mass, more than size alone, is where the Sun asserts its dominance. The Sun contains about 1.99 10^30 kilograms of matter. Proxima Centauri contains about 12% of that mass. This difference in mass affects everything. Gravity at the Sun's surface is stronger, escape velocity is higher. The Sun can hold on to its outer layers more firmly. Proxima's lower mass means weaker gravity overall, though its smaller radius partially compensates, making its surface gravity not as weak as the size comparison alone might suggest. Internally, the two stars are structured very differently. The Sun has a layered interior. At its centre is the core, where hydrogen fuses into helium. Surrounding that is a radiative zone, where energy moves outwards slowly through radiation. Beyond that lies a convective zone, where hot plasma rises and cooler plasma sinks, carrying energy to the surface. Proxima Centauri does not have this layered structure. It is fully convective. From its core to its surface, energy is transported by constant churning motion. This has profound consequences. Fully convective stars tend to have strong, tangled magnetic fields. Those magnetic fields drive stellar activity, including flares. While the Sun produces flares, Proxima Centauri produces them more frequently, and relative to its size more intensely. So while the Sun is far larger and brighter, Proxima Centauri can feel more restless. It experiences sudden increases in brightness when magnetic energy is released. These flares can dramatically affect any nearby planets, bathing them in bursts of radiation. This difference highlights an important point. Bigger does not mean more active in every sense. The Sun is larger and more powerful overall, but Proxima Centauri's internal dynamics give it a kind of volatility that the Sun does not usually display on the same relative scale. The lifespan of each star reflects these contrasts. The Sun is about 4.6 billion years old and roughly halfway through its stable life. In another 5 billion years or so, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf. Its total lifespan will be on the order of 10 billion years. Proxima Centauri's future stretches far beyond that. Its slow fusion rate means it can continue burning hydrogen for trillions of years. It will outlive the Sun by a factor of hundreds. In a distant future where galaxies have changed shape and star formation has slowed dramatically, Proxima-like stars may still be shining while Sun-like stars are long gone. Here, size intersects with time. This Sun's greater mass allows it to shine brightly but shortens its life. Proxima's modest mass limits its brightness, but grants it extraordinary longevity. One star trades intensity for endurance, the other does the opposite. Another way to compare the two stars is through their influence on surrounding space. The Sun's gravitational reach extends far beyond the planets we commonly think about. Its gravity shapes the Kuiper belt, the Oort cloud, and the paths of long-period comets. It carves out a region of dominance that stretches for light years. Proxima Centauri's gravitational influence is more modest. Its planetary system is compact. Its habitable zone, the region where liquid water could exist on a planet's surface, lies extremely close to the star. Proxima b orbits at a distance much smaller than Mercury's orbit around the Sun. This closeness is necessary to receive enough warmth from a dim star. This difference in scale again traces back to size and mass. A larger, brighter star pushes its habitable zone outward. A smaller, dimmer star pulls it inward. The Sun allows planets to exist comfortably at a wide range of distances. Proxima Centauri compresses everything toward itself. If you were standing on a hypothetical planet orbiting Proxima Centauri, the star would appear much larger in the sky than the Sun appears from Earth, even though the star itself is smaller. This is a reminder that apparent size depends on distance. Proximity can compensate for physical scale, so which star feels bigger? From Earth's perspective, the Sun fills half a degree of sky. From Proxima b's perspective, Proxima Centauri would dominate the sky even more strongly. The experience of size is relational. This relational nature of size is easy to overlook. We tend to think of size as absolute, but in astronomy it is always contextual. The Sun is big compared to Proxima Centauri. Proxima Centauri is big compared to Earth. Earth is big compared to a human. Each comparison is true within its frame. Energy output reinforces this layered perspective. The Sun emits a steady, predictable flow of energy. Solar cycles cause some variation, but the overall output remains remarkably stable. This stability has been essential for life on Earth. Proxima Centauri's output is lower and more variable. Its flares introduce bursts of radiation that could challenge the development of life on nearby planets. Again, size plays a role. The Sun's larger size and layered structure helps smooth out its energy production. Proxima's compact, fully convective interior amplifies magnetic activity. It's tempting to see these differences as advantages or disadvantages, but they are better understood as trade-offs. The Sun provides a wide, stable habitable zone, but has a limited lifespan. Proxima Centauri offers extraordinary longevity, but concentrates its habitable zone close to a more active star. Even the colour of the two stars reflects their size and temperature. The Sun's light contains a broad spectrum of wavelengths, producing white light. Proxima's cooler surface shifts its emission toward red and infrared. To a human observer adapted to Earth's daylight, Proxima's light would feel dim and unfamiliar. Yet for planets orbiting red dwarfs, that light would be normal. Photosynthesis, if it exists there, might use different wavelengths. Biology, if it arises, would adapt to a different stellar environment. Once again, size shapes possibility. Comparing Proxima Centauri to the Sun also forces us to confront how unusual our home star might be. While it feels ordinary to us, Sun-like stars are less common than red dwarfs. The galaxy is dominated by stars closer in size to Proxima than to the Sun. In that sense, Proxima Centauri represents the statistical norm, while the Sun represents a minority case. This inversion can be quietly unsettling. We often assume our experience is typical. Astronomy repeatedly shows us that it is not. So when we ask how big Proxima Centauri is compared to the Sun, the answer is clear in physical terms. It is much smaller. It has less mass, less volume, and far lower luminosity. But when we expand the comparison to include time, stability, and frequency, the picture becomes more balanced. Proxima Centauri is small but enduring, quiet but numerous, dim but persistent. The Sun and Proxima Centauri are not competitors. They're expressions of different solutions to the same fundamental problem: how to shine as a star. Holding these two objects side by side helps ground the idea of size in something tangible. It shows us that bigness is not a single axis, but a collection of properties that interact in complex ways. Numbers behave strangely once stars enter the conversation. They stop acting like simple labels and start revealing patterns that don't always match intuition. This becomes especially clear when we focus on three properties that sound straightforward on their own but behave in unexpected ways when combined: mass, radius, and size. In everyday life, heavier things are usually larger, and larger things usually take up more space. With stars, those relationships loosen, bend, and sometimes reverse, and Proxima Centauri sits at an especially interesting intersection of those effects. Mass is the place to start, because in stellar physics it sits at the root of nearly everything else. A star's mass determines how strongly gravity pulls inward, how tightly matter is compressed in the core, how fast nuclear fusion proceeds, and ultimately how the star will live and die. Radius, on the other hand, tells us how spread out that mass is. Two stars can contain very different amounts of matter, but still end up with similar radii, or the same mass but very different sizes. This disconnect is where the strangeness of stellar size begins to show itself. Proxima Centauri contains about 12% of the Sun's mass. That figure alone places it firmly in the category of low-mass stars, but not at the extreme lower limit. Below about 8% of the Sun's mass, objects cannot sustain steady hydrogen fusion. They become brown dwarfs, glowing faintly but never fully igniting. Proxima sits comfortably above that threshold. Gravity compresses its core enough for hydrogen atoms to fuse into helium, releasing energy that balances the inward pull of gravity. That balance is what defines a star. Despite having far less mass than the Sun, Proxima Centauri does not shrink proportionally in size. Its radius is about 14% of the Sun's, which is slightly larger than you might expect if size scaled neatly with mass. This mismatch hints at an important idea. As stars become less massive, they also become more compact. Their material is packed more tightly. Gravity squeezes harder relative to the amount of material present. This means Proxima Centauri is denser, on average, than the Sun. Not dramatically so, but enough to matter. Density affects internal pressure, energy transport, and magnetic behavior. It also means that surface gravity on Proxima is not as weak as its small size might suggest. If you could somehow stand on its surface, the pull downward would feel comparable to, or even slightly stronger than, the gravity you'd experience on the Sun's surface. Radius alone, then, is a misleading guide to scale. A smaller radius does not necessarily mean a gentler environment. Stellar size has to be interpreted through the lens of mass and density together. As we move down the mass scale from stars like the Sun to red dwarfs like Proxima, another important shift occurs. The internal structure of the star changes. The Sun has a radiative core and convective outer layer. Proxima Centauri is fully convective from center to surface. Energy is transported outward entirely through churning motion, rather than radiation slowly leaking through stable layers. This structural difference influences size in a subtle way. Fully convective stars can settle into a compact configuration that remains stable for extremely long periods. There are no layered boundaries to reorganize, no core that gradually accumulates helium in a way that forces expansion later on. Proxima's radius will remain relatively constant for most of its lifetime, slowly shrinking only as it exhausts hydrogen over trillions of years. So while the Sun will eventually swell into a red giant, increasing its radius by a factor of hundreds, Proxima Centauri will never experience anything like that dramatic growth. Its size is modest, but stable. The relationship between mass and radius also explains why red dwarfs cluster together in size. Once stars drop below about half the Sun's mass, adding or removing mass does not change radius very much. A star with 10% of the Sun's mass and one with 20% can end up with radii that are surprisingly similar. Gravity compresses the additional material more efficiently instead of allowing the star to expand. This effect gives rise to one of the counterintuitive truths of stellar physics. Some stars that are less massive than others can actually be smaller in radius than stars with even less mass. The details depend on composition, age, and internal temperature, but the general trend remains: Size is not a simple ranking from smallest mass to smallest star. Volume amplifies this effect. Because volume scales with a cube of the radius, small differences in radius correspond to enormous differences in volume. Proxima's radius being 14% of the Sun's means its volume is less than 0.3% of the Sun's. That tiny fraction contains 12% of the mass. The result is a star that is significantly more compact. This compactness has implications beyond internal physics. It affects how Proxima interacts with its surroundings. A smaller radius means a smaller surface area. Less surface area means less total energy can escape, even if the surface temperature was similar to the Sun's. In Proxima's case, the surface temperature is lower as well, compounding the effect. Mass and radius together also shape how stars respond to age. The Sun has been slowly increasing in luminosity over billions of years as its core composition changes. Its radius has expanded slightly, and it will continue to do so. Proxima's evolution is far more gradual. Its fusion rate changes so slowly that on human timescales, it is effectively static. In that sense, Proxima's size is not just small, it is patient. Another layer of strangeness appears when we widen the comparison beyond Proxima and the Sun. There exist stars with masses similar to the Sun but radii dozens or hundreds of times larger. Red giants and supergiants can be physically enormous, while having relatively modest masses compared to their size. Their outer layers are inflated, tenuously bound by gravity, and extremely low in density. A red giant might engulf the orbit of Earth while containing only a few times the Sun's mass. This flips everyday expectations completely. A star can be massive but compact, like Proxima relative to its mass. Or it can be massive and swollen like a supergiant. Or it can be low mass and compact like a red dwarf. Size alone tells you very little unless you also know mass and evolutionary stage. There are even stranger cases at the extreme end. White dwarfs pack roughly the Sun's mass into a volume comparable to Earth's. Neutron stars compress more mass than the Sun into a sphere only tens of kilometers across. In those objects, gravity overwhelms all other forces, and size becomes an entirely different concept. Compared to them, Proxima Centauri seems comfortably ordinary. Yet it is precisely this ordinariness that makes Proxima so valuable. It sits in a regime where the physics is extreme enough to be interesting, but stable enough to study. Its mass and radius place it in a category where small changes matter, but not so much that the star becomes exotic or unstable. Understanding Proxima's size also requires acknowledging how astronomers measure these properties. Radius is often inferred from luminosity and temperature. If you know how much energy a star emits and how hot its surface is, you can calculate how large its emitting surface must be. Mass is often determined through gravitational effects, such as how a star moves in response to companions or how it influences orbiting planets. In Proxima's case, its mass has been refined using observations of Proxima B's orbit. The way the planet tugs on the star reveals how massive the star must be. These measurements are indirect, but they are grounded in well-tested physics. What emerges from all this is a picture where small does not mean simple. Proxima Centauri's modest mass leads to a compact radius. That compact radius leads to higher density. Higher density supports full convection. Full convection supports magnetic activity. Magnetic activity produces flares. Flares influence planets. Each link traces back eventually to mass and radius. So when we talk about Proxima's size, we are really talking about a web of relationships. The star's mass determines its radius. The radius determines its surface area. The surface area limits energy output. Energy output shapes the habitable zone. The habitable zone defines where planets might exist. Size, in this sense, is not a static measurement but a starting condition. This web also highlights why size comparisons can feel unsatisfying if they stop at a single number. Saying Proxima is 14% the Sun's radius is accurate, but incomplete. Saying it is 12% the Sun's mass adds clarity. Understanding how those two numbers interact reveals much more. It's also worth noticing how these ideas quietly shift perspective. Proxima Centauri is not small in the way a pebble is small. It is small relative to a very specific reference point. Change the reference, and the meaning changes. Compared to Earth, Proxima is vast. Compared to the smallest stars capable of fusion, it is comfortably large. Compared to the Sun, it is modest. This relativity of size is one of the reasons astronomy can feel disorienting at first and soothing later on. Once you accept that there is no single scale that defines everything, the comparisons stop feeling competitive. Objects simply occupy different niches. Imagine trying to explain the size of an ocean to someone who has only ever seen a glass of water. The numbers might be accurate, the comparisons technically correct, but without some bridge to everyday experience, the meaning slips away. This is the challenge we face when we try to understand Proxima Centauri using human intuition. Stellar measurements are precise, but they live far outside the scale our senses evolved to handle. So one of the most effective ways to make sense of Proxima's size is not by adding more equations, but by translating what we know into references that the human mind can hold on to, at least briefly. Let's begin with something familiar: Earth. Our planet feels large to us because it contains everything we know directly. Continents, oceans, weather systems, cities and lives all unfold across its surface. Earth's diameter is about 12,700 kilometers. That number feels substantial until it's placed next to almost anything astronomical. Proxima Centauri's radius is roughly 100,000 kilometers, meaning its diameter is about 200,000 kilometers. You could line up Earth across Proxima's width more than 15 times. Even this small star could swallow our entire planet without much effort, and still have room left over. That comparison alone already stretches the imagination, but it is only the first step. Earth is not a star. It does not generate energy through nuclear fusion. Its mass, while enormous by human standards, is negligible next to stellar objects. Proxima Centauri contains roughly 40,000 times the mass of Earth. That mass is compressed into a sphere only a few 100,000 kilometers wide. Gravity does the rest, pulling matter inward until fusion ignites at the core. Now consider the Moon. It feels smaller than Earth, quieter somehow, less imposing. The Moon's diameter is about 3,500 kilometers. Proxima Centauri could fit the Moon across its diameter nearly 60 times. These numbers are not meant to impress so much as to recalibrate. They remind us that even the smallest stars exist on a scale that dwarfs planetary objects completely. Yet planets are still too abstract for many people. We don't encounter planets directly. Buildings, mountains, and cities are more grounded in experience. So let's bring the scale down again. Mount Everest rises about 8.8 kilometers above sea level. It feels enormous when viewed from the ground, dominant and immovable. Proxima Centauri's radius is over 11,000 times taller than Everest. If Everest were a grain of sand, Proxima would still be a massive structure stretching far beyond the horizon. The comparison is not meant to trivialize Earth's features, but to show how dramatically different stellar and terrestrial scales truly are. Cities offer another useful reference. A large city might span 50 or 60 kilometers from one end to the other. Some metropolitan areas stretch farther, but still remain within a few hundred kilometers. Proxima Centauri's radius alone could cover thousands of such cities laid end to end. The entire surface area of Earth, every city, ocean, and forest combined, could fit onto Proxima's surface many times over. At this point, it might feel like we've established the obvious. Proxima Centauri is huge compared to human-scale objects, but there is a subtle trap here. These comparisons, while accurate, can accidentally reinforce the idea that Proxima is enormous in an absolute sense. In astronomy, it is not. It is small for a star. This tension between human scale and cosmic scale is where the real insight lives. To explore that tension, it helps to shrink the universe instead of enlarging the star. Imagine scaling the Sun down to the size of a large exercise ball, about 65 centimeters in diameter. At that scale, Earth would be roughly the size of a peppercorn, orbiting about 23 meters away. Now imagine Proxima Centauri scaled down using the same ratio. It would be about the size of a grapefruit or a small orange. Notice what happens here. Proxima is still clearly a star-sized object in this miniature universe. It is not reduced to dust or debris. It is smaller than the Sun, yes, but still substantial. This scaled-down view is one of the most effective ways to reconcile the conflicting impressions of Proxima's size. On a human scale, it is overwhelmingly large. On a stellar scale, it is modest. Both are true at the same time. Distance also plays an important role in how we perceive size, even when we are aware of the numbers. Proxima Centauri is the closest star to the Sun, yet it is still so far away that its physical size has almost no effect on how it appears to us. To the naked eye, it is invisible. Through a telescope, it appears as a faint point of light. Its angular size, the amount of sky it occupies, is tiny. If Proxima Centauri were magically placed at the same distance as the Sun filling our sky, it would look very different. Its disk would be smaller than the Sun's, but still large enough to dominate the sky. Daylight under Proxima would be dimmer and redder. Shadows would be softer. The world would feel different, even though the star itself would still be far larger than anything on Earth. This thought experiment highlights another human bias. We associate visual dominance with importance. The Sun feels big because it fills our sky and shapes our daily experience. Proxima does not feel big because it does neither. But physical size is independent of how an object appears from a particular vantage point. There is also the issue of time, which quietly influences how we relate to scale. Human lives unfold over decades, civilizations over centuries or millennia. Proxima Centauri's lifespan is measured in trillions of years. Its size cannot be separated from that endurance. A small, stable star is able to persist far longer than a larger, more energetic one. From a human perspective, that longevity is difficult to internalize. We're used to thinking of large things as lasting longer. In stars, the opposite is often true. This reversal can feel counterintuitive until you frame it properly. A campfire burns bright and hot but consumes its fuel quickly. A candle burns dimmer but lasts longer. Proxima Centauri is closer to the candle. The Sun is closer to the fire. Both produce light and heat. One does so more intensely, the other more patiently. Another way to bring Proxima's size into human terms is to think about travel, even though such travel remains hypothetical. If you could fly around Proxima Centauri at the speed of a commercial airplane, about 900 kilometers per hour, it would take more than 25 years to circle the star once. That's without stopping, without resting, just moving steadily along its circumference. And this is the smaller of the two stars we're comparing. Even at the speed of sound, it would take years. At the speed of the fastest spacecraft humanity has ever built, it would still take weeks. These comparisons are not about feasibility. They're about grounding the concept of size in durations that feel real. Surface gravity adds another human-scale layer. On Earth, gravity is familiar and constant. We feel its pull in every movement. On Proxima Centauri, surface gravity would be stronger than Earth's, but not crushingly so. You would not be flattened instantly. You would simply weigh more. This is surprising to many people, who assume that a smaller star must have weaker gravity. Again, density matters. Proxima's mass is packed into a smaller volume, increasing the gravitational pull at its surface. This reinforces an important lesson. Size alone does not determine experience. Two objects can be very different in scale but produce comparable effects locally. Proxima is smaller than the Sun, yet its surface gravity is of the same order. Its magnetic activity can be more intense. Its flares can be proportionally stronger. Even the idea of standing on Proxima is itself misleading. Like all stars, Proxima does not have a solid surface. Its outer layers are plasma. The concept of standing there is purely hypothetical, but the physics still tells us something meaningful about scale and force. Another human-scale anchor is energy usage. The Sun provides about 1,360 watts per square metre at Earth's distance. Proxima Centauri provides far less energy overall, but planets orbiting close to it could receive similar amounts per square metre. This is why Proxima b can exist in a habitable zone despite the star's small size. Distance compensates for luminosity. From the perspective of a planet orbiting Proxima, the star would not feel small. It would dominate the sky, govern climate, and define time just as the Sun does for us. Days and years would be shaped by Proxima's presence. Seasons, if they exist, would depend on its energy output and activity. This shift in perspective is critical. Size is not just a number, it is an experience. And experience depends on position. Humans evolved under a sun-like star. Our senses, biology, and intuitions are tuned to that environment. When we encounter a star like Proxima Centauri, our first instinct is to judge it against that baseline: smaller, dimmer, less powerful. But for any life that might exist near Proxima, the star would be the centre of everything. It would not feel small at all. So seeing Proxima through human scales is not about forcing it into our familiar categories. It is about recognizing the limits of those categories. Earth-scale objects help us grasp how enormous Proxima is in absolute terms. Stellar comparisons help us understand how modest it is among stars. Planetary perspectives remind us that importance is relative. All of these views coexist. None cancels out the others. Measuring something you cannot touch, approach, or see as anything more than a faint point of light requires a very different mindset from measuring objects on Earth. There are no rulers stretched across space, no tape measures looped around stellar edges. Instead, astronomers rely on patience, geometry, physics, and inference, building a picture of a star piece by piece from the way it behaves and the way its light reaches us. Proxima Centauri, despite being our nearest stellar neighbour, still demands this indirect approach, and understanding how its size is measured reveals just how carefully constructed our knowledge really is. The first challenge is visibility. Proxima Centauri does not present a visible disk, even through most telescopes. Unlike the Sun, whose surface can be resolved and studied in detail, Proxima appears as a point of light. Its apparent size on the sky is far too small for direct measurement with conventional imaging. That means astronomers cannot simply photograph Proxima and measure its width. Everything must be inferred from secondary effects. Distance is the foundation of all stellar measurements, so that is where astronomers begin. If you do not know how far away a star is, you cannot accurately determine how bright it truly is, and without true brightness, size remains ambiguous. Proxima Centauri's distance is measured using stellar parallax, one of the oldest and most reliable methods in astronomy. Parallax relies on geometry rather than assumptions. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of much more distant stars. This shift is tiny, measured in fractions of an arcsecond, but it is measurable with precise instruments. By tracking Proxima Centauri's apparent movement over the course of a year, astronomers can calculate its distance using simple trigonometry. Proxima's parallax is relatively large compared to most stars, which is one of the benefits of its proximity. This gives astronomers a very accurate distance measurement, forming a solid base for everything that follows. Once distance is known, apparent brightness can be converted into luminosity. Apparent brightness tells us how much light reaches Earth. Luminosity tells us how much light the star actually produces. The difference between the two is distance. A dim-looking star can be intrinsically bright but far away, or intrinsically faint but nearby. In Proxima Centauri's case, even after correcting for distance, the star remains faint. That immediately tells astronomers it produces far less energy than the Sun. Luminosity alone still does not give size, but it narrows the possibilities. To move closer to radius, astronomers need temperature. A star's surface temperature can be determined by analysing its spectrum, the way its light is spread across different wavelengths. When starlight is passed through a spectrograph, it produces a pattern of dark absorption lines and bright regions. These patterns reveal which elements are present and how hot the star's surface is. Proxima Centauri's spectrum shows it is cool by stellar standards. Its peak emission lies in the red and infrared part of the spectrum. From this, astronomers can determine an effective surface temperature. Once luminosity and temperature are known, radius follows from a well-established physical relationship. Hotter objects emit more energy per unit surface area than cooler ones. If you know how much total energy a star emits, and how much energy each square meter of its surface emits, you can calculate how much surface area the star must have. From surface area, radius is straightforward. This method does not involve guessing. It is grounded in thermodynamics and radiation physics. The same principles apply whether you are measuring a light bulb filament or a star thousands of trillions of kilometers away. Proxima Centauri's low luminosity and low surface temperature combine to indicate a small radius. Mass is measured differently. Mass reveals itself through gravity. A star's mass determines how strongly it pulls on nearby objects. If a star has companions, whether other stars or planets, its mass can be inferred by observing their motion. Proxima Centauri is especially helpful in this regard because it hosts at least one known planet, Proxima b. As Proxima b orbits the star itself does not remain perfectly still. Both objects orbit a common center of mass. This causes Proxima Centauri to wobble slightly. By measuring shifts in the star's spectrum caused by this wobble, astronomers can estimate how massive the star must be to produce the observed motion. This technique, known as the radial velocity method, has become one of the most powerful tools in modern astronomy. The accuracy of Proxima's mass measurement has improved significantly since the discovery of its planet. Earlier estimates relied on stellar models and comparisons to similar stars. Now, those models can be tested against direct gravitational evidence. The result is a mass estimate that is far more secure than it once was. Another method, though more challenging, involves interferometry. Interferometers combine light from multiple telescopes to achieve the resolving power of a much larger instrument. In some cases, this allows astronomers to measure the angular diameter of nearby stars directly. Proxima Centauri is a difficult target for this technique because it is faint and small, but advances in instrumentation have made even these measurements possible at the limits of current technology. When interferometric measurements are available, they provide a direct check on radius estimates derived from luminosity and temperature. Agreement between these methods increases confidence. Discrepancies prompt refinement of models. Science advances not by assuming one method is perfect, but by comparing many. Models play a central role throughout this process. Stellar models are not arbitrary. They are built from fundamental physics, including gravity, nuclear fusion rates, energy transport, and the behavior of matter under extreme conditions. When astronomers input a star's mass and composition into these models, they can predict its radius, luminosity, temperature, and evolution over time. Observations then test those predictions. Proxima Centauri has been studied long enough that its observed properties fit well within these models. Its mass, radius, luminosity, and temperature all align with expectations for a red dwarf of its type. That consistency matters. It tells astronomers they are not forcing the numbers to fit a preconceived idea. The measurements support one another. It is also worth noting what astronomers do not rely on. They do not assume stars are uniform. They do not assume brightness equals size. They do not assume proximity makes things simpler. Each assumption is tested against observation. Proxima Centauri's faintness could have meant it was distant and large. Its proximity ruled that out. Its spectrum confirmed its low temperature. Its planetary system confirmed its mass. Each step constrained the possibilities. Uncertainty is an unavoidable part of this work. Measurements come with error bars. Distances have uncertainties. Temperatures have ranges. But these uncertainties are quantified, not ignored. Over time, as instruments improve, those ranges shrink. Proxima Centauri's parameters today are known with far greater precision than they were a century ago, not because the star changed, but because our methods did. Time itself plays a role in measurement. Observing stellar motion requires patience. Parallax measurements require a full orbit of Earth. Radial velocity measurements require many observations spread over months or years. Stellar activity cycles must be averaged out to reveal underlying properties. Proxima's frequent flares complicate measurements, introducing noise that must be carefully filtered. This is where astronomy becomes as much about persistence as brilliance. The data accumulates slowly. Patterns emerge over years, sometimes decades. Proxima Centauri has been observed long enough that its variability is well characterized. Astronomers know how often it flares, how intense those flares tend to be, and how they affect measurements. That knowledge feeds back into improved estimates of size and mass. One particularly subtle aspect of stellar measurement is composition. The elements present in a star affect how light escapes its surface and how energy moves inside it. Proxima Centauri has a composition similar to the Sun's, but with differences that reflect its formation environment. These differences influence opacity, which in turn affects how radius relates to luminosity. Models account for this, refining size estimates further. What emerges from all these methods is not a single number pulled from thin air, but a converging set of values derived from independent lines of evidence. Distance, brightness, temperature, motion, and theory all point to the same conclusion. Proxima Centauri is a small, low-mass star with a compact radius. Understanding how these measurements are made also changes how we think about certainty. Astronomical knowledge is often portrayed as distant or abstract, but in reality it is built on repeated checks and balances. Each property reinforces the others. When one measurement changes, others are re-examined. This dynamic process is how confidence grows. There is also a quiet humility embedded in these methods. Astronomers accept that they are inferring properties from light that left a star years ago. They accept that models are approximations, not perfect representations, and yet, within those constraints they extract remarkably precise information. The size of a star dozens of trillions of kilometers away can be known to within a few percent. This ability to measure the unapproachable is one of the quiet triumphs of science. It allows us to talk meaningfully about Proxima Centauri's size without ever seeing it as anything more than a point of light. Importance does not always announce itself with brightness or scale, and Proxima Centauri is a quiet demonstration of that fact. On paper, it looks unimpressive when placed beside stars like the Sun. It has less mass, a smaller radius, and produces only a tiny fraction of the energy. If stars were ranked by spectacle alone, Proxima would sit far from the top, and yet, in modern astronomy, it occupies a position of outsized significance. Understanding why requires stepping away from intuition and looking carefully at how the universe actually distributes its stars, its time, and its opportunities. To begin with, Proxima Centauri is small because the physics of star formation favours small outcomes far more often than large ones. When clouds of gas collapse to form stars, they fragment. Turbulence, rotation, magnetic fields, and radiation pressure all work together to break large clouds into many smaller clumps. Most of those clumps never gather enough mass to form sun-like stars. Instead, they form red dwarfs. This is not an accident or an exception, it is the dominant result. In the Milky Way, red dwarfs make up roughly 70 to 80% of all stars. That means the galaxy is not primarily defined by stars like the Sun, even though those stars are easier to see and study from afar. It is defined by stars like Proxima Centauri, small, cool, faint and long-lived. Proxima matters because it is typical, not because it is extreme. This alone elevates its importance. When astronomers want to understand the galaxy as a whole, they cannot focus only on bright stars. They need representatives of the most common stellar populations. Proxima Centauri offers that representation at a distance close enough to allow detailed study. It serves as a local example of what most stars in the Milky Way are actually like. Its small size is central to this role. A red dwarf's low mass leads to slow fusion. Slow fusion leads to long lifespans. Proxima Centauri will burn hydrogen for trillions of years, far longer than the Sun will remain stable. This longevity means that red dwarfs dominate the future of the galaxy. Long after larger stars have evolved, exploded, or faded, stars like Proxima will still be shining. That future-focused perspective is easy to miss because human timescales are so short. From our point of view, 5 or 10 billion years already feels unimaginably distant. Trillions of years barely register. But on cosmic scales, that endurance is enormous. Proxima Centauri is small, but it is patient, and patience matters in a universe where time stretches far beyond any biological frame of reference. Its importance also comes from accessibility. Proxima Centauri is close. That closeness turns it into a laboratory. Observations that would be impossible for distant red dwarfs become feasible here. Astronomers can monitor its flares, track its rotation, measure its magnetic field, and observe its interactions with orbiting planets in ways that are far more difficult for similar stars hundreds of light years away. Distance amplifies importance. A small star far away might remain statistically interesting but practically unreachable. Proxima Centauri's proximity bridges that gap. It allows astronomers to test theories of red dwarf behavior using real data, rather than relying entirely on models. Another reason Proxima Centauri matters lies in the way its small size shapes its planetary system. Proxima b, the Earth-sized planet orbiting within its habitable zone, exists only because the star is small and dim. A Sun-like star would require planets to orbit farther out to maintain similar temperatures. Proxima's low luminosity pulls its habitable zone inward, placing it extremely close to the star. This closeness creates challenges. Proxima b is likely tidally locked, showing the same face to the star at all times. It may be exposed to frequent stellar flares. Its atmosphere, if it has one, must survive intense radiation and particle storms. None of this sounds gentle, but these challenges are precisely why Proxima is important. If planets can maintain atmospheres and potentially support life under these conditions, then the number of potentially habitable worlds in the galaxy increases dramatically. Since red dwarfs are so common, even a modest success rate would imply vast numbers of Earth-sized planets in habitable zones. Proxima Centauri becomes a test case. Its small size creates a demanding environment. If life-friendly conditions can exist there, they may exist in many places. This makes Proxima Centauri relevant not just to stellar physics, but to astrobiology. Its size influences its radiation output. That radiation output influences atmospheric chemistry. Atmospheric chemistry influences surface conditions. Each step traces back to the star's modest mass and radius. The star's magnetic activity, another consequence of its small size and fully convective interior, adds another layer. Proxima produces strong flares that can temporarily increase its brightness by orders of magnitude. These flares can strip atmospheres, alter chemistry, and challenge biological stability. At the same time, they provide energy that could drive complex reactions. The balance between destruction and opportunity is not yet fully understood. Again, Proxima's importance lies in the questions it raises. It forces astronomers to refine their understanding of habitability. It prevents simplistic assumptions. A planet in a habitable zone around a red dwarf is not equivalent to Earth around the Sun. The details matter, and Proxima offers a nearby case study where those details can be examined. There is also an observational reason Proxima's size matters. Smaller stars make it easier to detect planets. When a planet orbits a small star, its gravitational effect is more pronounced. Its transit, if it passes in front of the star, blocks a larger fraction of the star's light. Its influence on stellar motion is easier to measure. This detection advantage is one reason why so many known exoplanets orbit red dwarfs. Proxima Centauri benefits from this effect. Its small size allowed astronomers to detect Proxima b using subtle shifts in the star's spectrum. Larger stars would hide such signals more effectively, so Proxima's modest dimensions directly enabled one of the most significant exoplanet discoveries to date. Beyond planets, Proxima's importance extends to stellar evolution models. Red dwarfs challenge certain assumptions because they evolve so slowly. Their interiors remain stable for immense periods. Their fusion processes proceed at rates that test long-term predictions. Proxima provides an anchor point for those models. Observations can be compared to theory over decades, revealing whether predictions hold. This slow evolution also makes Proxima a useful reference for studying magnetic cycles and stellar aging. Because its properties change so gradually, variations in activity can be studied without the complication of rapid structural evolution. Its size contributes to this stability, making it a steady subject rather than a rapidly changing one. There is a cultural dimension as well. Proxima Centauri occupies a unique place in human imagination because it is both close and alien. It is not like the Sun, yet it is near enough to feel relevant. Discussions of future interstellar travel often focus on Proxima because it is the nearest star system with a known, potentially rocky planet. Its small size does not diminish its role as a destination or a symbol. If anything, it makes it more approachable, at least conceptually. That symbolic role feeds back into scientific interest. Missions, proposals, and thought experiments often center on Proxima precisely because it is small, nearby, and representative. It offers a realistic target for future technologies. A massive, distant star would not serve the same purpose. Another subtle aspect of Proxima's importance lies in contrast. Comparing it to the Sun helps astronomers understand what makes the Sun unusual. Sun-like stars are brighter, larger, and shorter-lived than red dwarfs. They provide wide habitable zones but limited time. Proxima highlights these trade-offs. By studying what Proxima is not, scientists better understand what the Sun is. This comparative approach is foundational in science. Differences reveal structure. Proxima's small size accentuates the Sun's relative largeness. The Sun's brightness highlights Proxima's faintness. Each star defines the other through contrast. There is also an ecological analogy worth considering without drifting into abstraction. In many ecosystems, small organisms dominate in number and longevity, while large organisms dominate attention. In forests, grasses and insects outweigh large animals in biomass and persistence. Stars follow a similar pattern. Red dwarfs are the grasses of the galaxy. Sun-like stars are the trees. Proxima Centauri matters because it represents the dominant background against which everything else exists. Even in galactic structure, red dwarfs contribute significantly to mass distribution. While each individual star is small, their sheer number means they collectively shape the galaxy's gravitational field. Proxima is one data point in that vast population, but its proximity allows it to stand in for many others. From an educational standpoint, Proxima Centauri also plays a crucial role. It challenges the assumption that bigger is better or more important. It encourages a more nuanced view of scale and significance. This is not just philosophically satisfying, it is scientifically necessary. The universe does not organize itself around human preferences. So Proxima is small because star formation favors low-mass outcomes, because gravity and fusion balance at lower thresholds more often than higher ones, and because the galaxy is built from many modest components rather than a few dominant ones. Proxima is important because it is close, common, long-lived, and capable of hosting planets in conditions that test our understanding of habitability. These two facts are not in tension, they are connected. Its small size is precisely what allows it to play such an important role. It lasts longer, it is more typical, it is easier to study nearby planets, it remains stable over immense periods. Time behaves differently when you step away from human clocks and look at it through the life of a star like Proxima Centauri. What feels unimaginably slow to us is simply the natural pace of events for a red dwarf. There is no rush built into its structure, no dramatic urgency pushing it toward a quick transformation. Instead, everything unfolds gradually, governed by a balance between gravity and nuclear fusion that changes so slowly it is almost static on any scale we recognize. Proxima Centauri began its life much like other stars, forming from a collapsing cloud of gas and dust. Gravity pulled material inward, compressing it until temperatures and pressures at the center became high enough for hydrogen fusion to ignite. That ignition marked the beginning of its life as a star. For a brief period, it may have been more active than it is now, rotating faster and producing stronger flares. Young red dwarfs tend to be restless, but even in its youth, Proxima was already set on a very different path from stars like the Sun. The key difference lies in mass. With only about 12% of the Sun's mass, Proxima Centauri never developed the intense core pressures that drive rapid fusion. Hydrogen fusion began, but at a measured pace. Each fusion reaction releases energy, and that energy pushes outward, balancing gravity's inward pull. In Proxima's case, that balance is gentle rather than explosive. Fusion proceeds steadily, quietly, without dramatic swings in output. This slow fusion rate defines almost everything about Proxima's life. Because it burns its fuel so conservatively, it wastes very little energy. Where the Sun converts hydrogen into helium at a rate that will exhaust its core in roughly 10 billion years, Proxima Centauri's hydrogen supply will last for trillions, not millions, not billions, trillions. To put that in perspective, the universe itself is only about 13.8 billion years old. Proxima Centauri has barely begun its life. From the star's point of view, the current age of the cosmos is an early chapter, not a midpoint. It will continue shining long after galaxies like ours have changed beyond recognition. Another factor contributing to this longevity is Proxima's internal structure. Being fully convective means that material from the surface and the core is constantly mixed. Hydrogen from the outer layers can be carried inward, replenishing the fuel supply. Helium produced in the core does not remain trapped in one place. This mixing prevents the buildup of an inert helium core that would eventually force the star to expand. As happens in Sun-like stars, the Sun's fate is sealed by its layered structure. As helium accumulates in its core, fusion gradually shifts outward, causing the star to swell into a red giant. Proxima Centauri avoids this entirely. There is no distinct boundary between core and envelope. No single region where fuel becomes isolated and exhausted. As long as hydrogen remains anywhere in the star, fusion can continue. This makes Proxima's life remarkably uneventful in the best possible way. It does not undergo dramatic phases, it does not swell to enormous size, it does not explode, it simply continues stable and persistent. Yet, uneventful does not mean inactive. Proxima Centauri is magnetically lively. Its fully convective interior generates strong magnetic fields. These fields twist and tangle, storing energy that is occasionally released as flares. Over short timescales, Proxima can appear quite dramatic. Its brightness can increase suddenly, particularly in ultraviolet and X-ray wavelengths. These outbursts can affect nearby planets significantly. Over long timescales, however, these flares do not change the star's fundamental nature. They are surface phenomena, expressions of magnetic dynamics rather than signs of structural instability. Proxima survives them easily, returning again and again to its steady baseline state. Rotation plays a role here as well. Proxima Centauri rotates more slowly than it likely did in its youth, having lost angular momentum over time through interactions between its magnetic field and stellar wind. This gradual slowing is another marker of age, but it happens so slowly that even billions of years produce modest changes. The star's rotation period is measured in weeks, not hours, and it will continue to slow gradually over time. This slow rotation contributes to magnetic behavior, but does not disrupt the star's stability. In fact, it reinforces the sense that Proxima is settled into a long-term equilibrium. The processes governing its life are not racing toward an endpoint. They are balanced in a way that allows for immense duration. If we imagine the life of a star as a story, Proxima Centauri's story is not driven by plot twists. It is driven by persistence. Each moment looks much like the last. Each million years blends into the next. The drama, if there is any, exists only in brief surface events that do not alter the overall trajectory. This long, slow life has profound implications for anything orbiting the star. Planets around Proxima exist in an environment that is stable over unimaginable spans of time. The star's energy output changes little over trillions of years. There is no looming red giant phase that will engulf inner orbits, no sudden supernova. The long-term environment is predictable in ways that are rare in cosmic terms. At the same time, the early life of a red dwarf can be challenging. Young red dwarfs are often more active, producing stronger and more frequent flares. Proxima likely went through such a phase early on. Any planets that formed during that time would have been exposed to intense radiation. Whether atmospheres could survive or recover from this period is an open question, and one that astronomers continue to explore. What matters for the long-term picture is that once a red dwarf settles down, it stays settled. Proxima Centauri today is still active compared to the Sun, but it is far calmer than it was in its youth. Over the trillions of years ahead, its activity will likely continue to decline slowly. The length of Proxima's life also reframes the idea of habitability. Life on Earth emerged relatively quickly once conditions stabilized, but complex life took billions of years to evolve. On a planet orbiting Proxima, there is no shortage of time. Even if early conditions were harsh, there are vast stretches of future stability during which life could potentially arise and adapt. This does not mean life must exist there. It simply means the window remains open far longer than it does around sun-like stars. Time becomes an asset rather than a limitation. There is also a broader cosmic implication. As the universe ages, star formation will slow, gas will be used up, massive stars will become rarer. In that distant future, red dwarfs will dominate the stellar population not just in number, but in visibility. They will be the primary sources of light in the universe. Proxima Centauri represents that future. It is an early example of the stars that will persist when others are gone. From this perspective, Proxima's small size is not a disadvantage. It is an adaptation. Smaller mass allows for slower fusion. Slower fusion allows for endurance. Endurance allows for relevance over vast timescales. This slow life also means Proxima changes very little from one human generation to the next. The star you would observe today is effectively the same star ancient observers would have seen had they been able to detect it, and it will be effectively the same star tens of thousands of years from now. That continuity gives astronomers a stable reference point. Stability, however, should not be confused with simplicity. The physics inside Proxima Centauri is complex. Fully convective interiors involve turbulent flows, magnetic interactions, and subtle feedback mechanisms. These processes are difficult to model precisely. Proxima's long life provides a testing ground for these models. If predictions hold true over decades of observation, confidence grows. The star's slow evolution also makes it easier to separate short-term variability from long-term trends. Astronomers can study flares, rotation, and magnetic cycles knowing that the underlying structure is not shifting dramatically beneath them. This clarity is valuable. Emotionally, there is something quietly grounding about a star that is not in a hurry. Human lives are filled with deadlines, transitions, and irreversible changes. Proxima Centauri exists outside that rhythm. Its timescale dwarfs urgency. It does not need to rush toward anything. It simply continues. This does not make it static. It still shines. It still flares. It still interacts with its planets. But it does so within a framework of extraordinary patience. At first glance, Proxima Centauri gives very little away. Its light is faint, steady most of the time, and easy to dismiss as unremarkable when compared to brighter stars. If you were able to observe it casually, without instruments sensitive to subtle changes, you might conclude that it is calm, perhaps even dull. But that impression only holds if you look briefly and without patience. When astronomers watch Proxima carefully, over long stretches of time and across many wavelengths of light, a more complicated personality emerges, one defined by long periods of quiet punctuated by sudden, intense outbursts. This contrast between steadiness and volatility is not a contradiction. It is a natural consequence of Proxima's size, structure, and internal dynamics. Understanding its temperament means holding both sides at once. Most of the time, Proxima glows gently, producing a relatively constant output of energy. Occasionally, however, it releases enormous amounts of stored magnetic energy in the form of flares, briefly transforming from a dim red point into one of the most energetic objects in its local environment. To understand why this happens, it helps to return to Proxima's interior. Unlike the Sun, which has distinct layers that transport energy in different ways, Proxima Centauri is fully convective. From its core to its outermost layers, hot plasma rises and cooler plasma sinks in a continuous cycle. This churning motion is not just a way of moving energy, it also generates powerful magnetic fields. Magnetic fields in stars are created by the movement of charged particles. In Proxima, the entire star participates in this process. There is no stable, layered region where magnetic fields can settle into simple patterns. Instead, the fields twist, tangle, and interact in complex ways. Over time, this tangled magnetic energy builds up stress, much like tension accumulating in a twisted rubber band. Eventually, that tension is released. When magnetic field lines suddenly rearrange themselves, large amounts of energy are freed almost instantaneously. This energy heats the surrounding plasma to extreme temperatures and accelerates particles to high speeds. The result is a stellar flare. Proxima Centauri is particularly prone to this behavior. Observations have shown that it flares frequently, especially in high-energy wavelengths such as ultraviolet and X-rays. Some of these flares are relatively modest, comparable to strong solar flares. Others are far more extreme, increasing Proxima's brightness by factors of hundreds or even thousands for brief periods. These outbursts can last from minutes to hours. During that time, the star's radiation environment changes dramatically. A planet orbiting nearby would experience a sudden surge of energetic photons and particles, far beyond the baseline conditions it usually receives. Yet between these flares, Proxima returns to its quiet glow. Its average energy output remains low and stable. Days, weeks, or even months can pass without any dramatic events. This dual nature is essential to understanding Proxima's temperament. It is not constantly violent, nor is it permanently calm. It exists in a state where long-term stability coexists with short-term unpredictability. The Sun, by comparison, also flares, but the scale and frequency are different. Solar flares are tied to an 11-year activity cycle, rising and falling in regular patterns. Proxima's activity does not follow such a simple rhythm. Its flares are more frequent relative to its size, and its magnetic cycles are less well understood. This is partly because Proxima's fully convective nature alters how magnetic fields evolve over time. Rotation plays a role here as well. Proxima Centauri rotates relatively slowly compared to its younger self, but it is still fast enough to sustain strong magnetic activity. As stars age and lose angular momentum, their rotation slows and magnetic activity tends to decrease. Proxima is partway along this path. It is calmer than it once was, but it has not become magnetically quiet. From a human perspective, this behavior can feel unsettling. We're accustomed to thinking of stability as smoothness. A stable system, in everyday terms, does not produce sudden bursts of energy. In stellar physics, stability means something different. It means the star does not tear itself apart. It means gravity and fusion remain in balance. Flares do not threaten that balance. They are surface-level events, not signs of structural instability. In fact, Proxima's ability to produce flares without disrupting its long-term behavior is a sign of how robust its internal balance is. The star absorbs and redistributes these energetic events without changing its overall trajectory. It remains the same star before and after each outburst. This distinction matters, especially when considering the environment around Proxima. Its planets, particularly Proxima b, live under this alternating pattern of calm and intensity. Most of the time, Proxima b receives a steady, modest flow of energy. Then, occasionally, it is bathed in radiation from a flare that can dwarf the star's usual output. Whether such conditions are hostile or merely challenging depends on many factors. Atmospheric thickness, magnetic shielding, chemical composition, and even geological activity all play roles. A thick atmosphere or a strong planetary magnetic field could absorb or deflect much of the harmful radiation. Without such protection, repeated flares could strip an atmosphere away over time. What makes Proxima especially interesting is that these questions are not hypothetical in a distant sense. Proxima b is close enough that astronomers can observe the star's flares directly and estimate their impact. This allows scientists to test models of atmospheric erosion and radiation exposure using real data rather than abstract scenarios. It is also important to remember that flares are not uniformly destructive. They can drive complex chemistry in planetary atmospheres. High-energy radiation can break apart molecules, creating reactive compounds that might otherwise never form. On Earth, lightning and ultraviolet radiation are thought to have played roles in prebiotic chemistry. In a different environment, stellar flares could play a similar role, though at a different scale. So Proxima's temperament cannot be reduced to dangerous or safe. It is conditional. It depends on context. It depends on timing. It depends on the resilience of any planets involved. From the star's perspective, these flares are brief interruptions in an otherwise steady existence. They do not accelerate its aging. They do not consume significant amounts of fuel. They are expressions of magnetic dynamics, not signs of exhaustion or instability. This pattern of behavior also affects how astronomers study Proxima. Measurements of brightness, temperature, and motion must account for flares. A single observation taken during an outburst could misrepresent the star's typical properties. As a result, astronomers rely on long-term monitoring to separate baseline behavior from transient events. Over years of observation, a clear picture has emerged. Proxima's average output is low. Its flares are frequent but short-lived. Its overall energy budget remains dominated by steady fusion rather than explosive events. This reinforces the idea that its small size and slow fusion rate govern its long-term behavior, even if surface activity adds complexity. There is also an evolutionary aspect to consider. Proxima's flares were likely more intense and more frequent in the past. Young red dwarfs are often highly active, producing powerful flares that can last for extended periods. As the star ages and its rotation slows, this activity gradually diminishes. Proxima appears to be past its most extreme phase, though it has not become fully quiet. This gradual calming over time introduces another layer to the story of habitability. A planet that survives the early, more violent period may eventually enjoy a long era of relative stability. The question becomes whether early conditions allow for recovery or adaptation. Again, Proxima's importance lies in the fact that it gives us a real example to study. Rather than speculating about red dwarf behavior in general, astronomers can examine Proxima directly. Its flares are observed, their energies are measured, their frequencies are catalogued, models are tested against reality. There is also a psychological aspect to how we perceive this temperament. Humans tend to associate calmness with safety and volatility with danger. Proxima defies that simple dichotomy. It is calm on average, volatile in bursts and stable overall. Holding these ideas together requires a shift in how we think about stellar behaviour. In some ways, Proxima's temperament mirrors the broader universe. Long periods of gradual change interrupted by sudden events. Galaxies evolve slowly, punctuated by mergers. Geological processes unfold over millions of years, punctuated by earthquakes and eruptions. Stability does not mean monotony, it means resilience. For Proxima Centauri, resilience is built into its small size. Lower mass means lower fusion rates. Lower fusion rates mean less internal stress. Less stress means a star that can absorb surface-level disturbances without altering its core balance. As observations continue, astronomers refine their understanding of how Proxima's magnetic fields behave, how flares scale with rotation and age, and how similar stars might behave elsewhere in the galaxy. Each new dataset adds nuance. The picture becomes more detailed, but also more realistic. It becomes clear that Proxima's quiet glow and sudden flares are not opposing traits. They are complementary expressions of the same underlying physics. The star is steady because it is small. It is active because it is fully convective. Both traits arise from the same origin. Instead of beginning with distance, it helps to begin with balance. The idea of a habitable zone is not about perfection or comfort, but about a narrow range where competing forces settle into a workable arrangement. Too much energy and water evaporates or escapes. Too little and it freezes solid. Around a star as small as Proxima Centauri, that balance is achieved in a way that feels unfamiliar, compressed inward by the star's modest output and shaped by behaviours very different from those of the Sun. The term habitable zone is often misunderstood as a promise. In reality, it is a starting condition. It describes a region around a star where a planet, assuming it has a suitable atmosphere, could maintain liquid water on its surface. That assumption matters. The star provides energy, but everything else depends on the planet itself. Composition, atmosphere, magnetic field, rotation, and geological activity all play critical roles. The star sets the stage, but it does not write the entire script. For Proxima Centauri, the stage is unusually compact. Because the star produces only a tiny fraction of the Sun's energy, a planet must orbit very close to receive enough warmth. Proxima's habitable zone lies only a few million kilometers from the star, far closer than Mercury's orbit around the Sun. In fact, a planet in Proxima's habitable zone would complete an orbit in just a few Earth weeks. This proximity changes everything about how the habitable zone behaves. Around the Sun and the habitable zone spans a relatively wide range of distances. Earth sits comfortably within it, while Mars lies near the colder edge and Venus just inside the hotter boundary. The Sun's large size and steady output allow this zone to be broad and forgiving. Proxima Centauri offers no such luxury. Its habitable zone is narrow. Move slightly too close and conditions become hostile. Move slightly too far and water freezes. This narrowness is a direct consequence of the star's size and luminosity. With so little energy to distribute, Proxima cannot support a wide range of orbital distances with Earth-like temperatures. Everything must be packed inward, close to the source. That closeness introduces a new factor that is mostly irrelevant in our solar system: tidal locking. A planet orbiting so close to its star is likely to become tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This is not a rare or exotic outcome. It is a natural result of gravitational interaction over time. At first, tidal locking sounds inhospitable. A permanent day side and a permanent night side suggest extreme temperature differences, one hemisphere scorched, the other frozen. But climate models complicate this picture. With a sufficiently thick atmosphere or a global ocean, heat can be redistributed. Winds and currents can carry warmth from the day side to the night side, softening extremes. So tidal locking does not automatically rule out habitability. It simply changes the conditions under which it must operate. The star's small size also means that the habitable zone lies within a region strongly influenced by stellar activity. Proxima's flares, discussed earlier, are not distant events. A planet in the habitable zone sits close enough that flares loom large. When Proxima releases a burst of energy, the planet receives it quickly and intensely. This raises concerns about atmospheric erosion. High-energy radiation can strip gases from a planet's atmosphere, especially if the planet lacks a strong magnetic field. Over time, repeated flares could thin or remove the atmosphere entirely, eliminating surface water regardless of distance. Yet here again, the situation resists simple conclusions. A planet with a dense atmosphere may absorb much of the radiation before it reaches the surface. A strong magnetic field can deflect charged particles. Volcanic outgassing can replenish lost gases. The outcome depends on a complex interplay of factors. The size of the star indirectly influences all of this. Proxima's lower mass means its habitable zone is close, which increases exposure to flares. Its fully convective interior increases flare frequency. But its long lifespan means there is also an immense amount of time for processes of loss and recovery to play out. Another often overlooked aspect of habitable zones around small stars is spectral energy distribution. Proxima emits much of its energy in infrared rather than visible light. This changes how a planet absorbs and reflects energy. Ice, for example, reflects visible light well, but absorbs infrared more efficiently. This can reduce the likelihood of runaway freezing on the night side of a tidally locked planet. Vegetation, if it exists, would also interact differently with this light. Photosynthesis around a red dwarf would not look like photosynthesis on Earth. It might use different pigments and operate under dimmer, redder illumination. The star's small size does not preclude energy availability. It reshapes it. There is also the question of stellar evolution. Proxima Centauri's luminosity changes very slowly over time. This stability is an advantage. Around Sun-like stars, increasing luminosity gradually pushes the habitable zone outward. Earth itself will eventually leave the Sun's habitable zone as the Sun brightens. Proxima's habitable zone remains relatively fixed for trillions of years. That long-term stability means that if conditions ever become suitable on a planet orbiting Proxima, they could remain suitable for immense spans of time. Evolution would not be rushed. There would be no looming stellar transformation forcing adaptation or extinction. However, this advantage comes with an early challenge. Red dwarfs are more active when young. Their early flares can be far more intense than what we observe today. The early habitable zone may have been bathed in harsh radiation. Any early atmospheres could have been stripped away. Whether planets can recover from this phase remains an open question. Some models suggest that planets forming farther out could migrate inward after the most active period. Others suggest that atmospheres could be rebuilt through volcanic activity or cometary impacts. Again, the star's small size shapes the problem, but does not determine the outcome alone. The concept of a habitable zone also assumes surface liquid water, which is a human-centric bias. Life elsewhere may not require the same conditions. Subsurface oceans protected beneath ice could exist even outside the traditional habitable zone. Around a star like Proxima, tidal heating from gravitational interaction could provide internal energy, warming a planet from within. This expands the notion of habitability beyond a simple ring around the star. Proxima's size and mass influence tidal forces. Strong tidal interactions could drive geological activity, maintaining heat and potentially supporting subsurface environments, even if surface conditions are harsh. The compact nature of Proxima's system also increases the likelihood of such interactions. Planets orbiting close together can gravitationally influence one another, sustaining eccentric orbits and ongoing tidal heating. This is seen in our own solar system among moons like Europa and Enceladus. So when we talk about the habitable zone around a tiny star, we are really talking about a collection of overlapping zones: radiative habitability, tidal habitability, atmospheric resilience. Each zone is shaped by the star's size, but none are defined by it alone. Proxima b sits squarely in the classical habitable zone based on distance and stellar output. That fact alone made headlines. But the deeper story lies in what that placement actually means. It does not guarantee oceans or life. It guarantees only that under the right conditions, liquid water could exist. This distinction is crucial. Popular descriptions often blur the line between habitable and inhabited. In scientific terms, the habitable zone is permissive, not predictive. It describes where life could exist, not where it does. Proxima's small size forces that distinction into the foreground. The star provides just enough energy, but in a concentrated and sometimes volatile way. It challenges planets to adapt rather than coddling them. There is also a practical reason astronomers care deeply about habitable zones around small stars: detection. Planets in close orbits are easier to find. Their gravitational influence is stronger. Their transits, if aligned correctly, block a larger fraction of starlight. Proxima b was discovered precisely because Proxima's size amplifies these signals. This observational bias means that much of what we know about potentially habitable exoplanets comes from red dwarf systems. Understanding how habitable zones function around stars like Proxima is therefore not optional. It is foundational. The star's size also affects the shape of its habitable zone in time. Because Proxima will shine steadily for trillions of years, its habitable zone does not rush outward or inward. It remains close and consistent. A planet that survives early challenges could enjoy stability unmatched around larger stars. From a cosmic perspective, this makes red dwarfs the long-term hosts of habitability in the universe. When larger stars fade, these small stars remain. If life can adapt to their environments, the universe may be far more hospitable over the long term than a sun-centered view would suggest. Emotionally, there is something counterintuitive about this idea. We tend to associate gentle environments with large, steady sources of energy. Proxima asks us to reconsider that association. Its environment is demanding but persistent, not forgiving but enduring. As research continues, models of Proxima's habitable zone grow more refined. They incorporate flare statistics, atmospheric chemistry, cloud formation, and magnetic shielding. Each addition adds complexity rather than certainty. The picture becomes richer, but never final. That lack of finality is appropriate. The habitable zone is not a static boundary. It is a dynamic region shaped by interactions between star and planet over time. Proxima Centauri's small size ensures those interactions are intimate, close, and intense. Discussions about Proxima Centauri tend to change tone the moment Proxima b enters the picture. The star itself is fascinating, but the presence of a nearby planet pulls the conversation into more familiar territory. Planets invite comparison. They invite imagination. They invite the question of place rather than process. Proxima b transforms Proxima Centauri from an interesting stellar object into a system, and that shift carries significant weight. Proxima b was discovered in 2016 using the radial velocity method, a technique that detects the subtle wobble of a star caused by the gravitational pull of an orbiting planet. The signal was small, buried in the noise created by Proxima's magnetic activity, but it was persistent. Careful analysis revealed a planet with a minimum mass similar to Earth's, orbiting its star every 11 days at just the right distance to fall within the star's habitable zone. That combination of factors immediately stood out: Earth-sized, habitable zone, near a star. Each element on its own would be noteworthy. Together, they created a rare alignment that reshaped priorities in exoplanet research. Before Proxima b, most potentially habitable exoplanets were distant and difficult to characterize. Proxima b changed that. Its proximity makes it, at least in principle, accessible to detailed observation. It is close enough that future telescopes may be able to study its atmosphere directly. It is close enough to serve as a benchmark rather than a statistical curiosity. Yet proximity does not equal familiarity. Proxima b is not a second Earth. Its environment is shaped by a star very different from the Sun, and its own properties remain largely unknown. The planet's mass is estimated, not precisely measured. Its radius is uncertain. Its composition, atmosphere, and surface conditions are still matters of active research. What is known, however, is that Proxima b orbits extremely close to its star. At that distance, tidal forces are strong. Over time, those forces almost certainly lock the planet into synchronous rotation. One side perpetually faces Proxima Centauri, the other faces away into darkness. This configuration fundamentally alters climate patterns. In such a scenario, the planet does not experience a familiar day-night cycle. Instead, there is a permanent day side, a permanent night side, and a twilight region between them. Climate models suggest that if the planet has a sufficiently thick atmosphere, winds could redistribute heat effectively, preventing atmospheric collapse on the night side and moderating temperatures on the day side. This possibility depends heavily on atmospheric composition. A thin atmosphere might freeze out on the dark side, causing gases to condense and fall out of circulation. A thicker atmosphere, rich in greenhouse gases, could maintain global circulation. Proxima b's atmosphere, if it exists, sits at the center of this uncertainty. The star's temperament complicates the picture. Proxima's frequent flares expose the planet to bursts of high-energy radiation. Over time, such radiation can erode atmospheres, particularly lighter gases like hydrogen. If Proxima b lacks a strong magnetic field, its atmosphere may be especially vulnerable. On Earth, the magnetic field plays a crucial protective role. It deflects charged particles from the solar wind, preserving the atmosphere over billions of years. Whether Proxima b has a similar field is unknown. Its mass suggests it could generate one, but tidal locking might reduce internal rotation, weakening the dynamo that creates magnetic fields. Even if Proxima b's original atmosphere was stripped away early in its history, that does not necessarily mean it is barren today. Volcanic outgassing could replenish gases, cometary impacts could deliver volatiles, geological activity could recycle material between interior and surface. The long lifespan of Proxima Centauri allows time for recovery, adaptation, and stabilization. Another factor often overlooked is water inventory. Planets forming around red dwarfs may begin with larger amounts of water than Earth. If Proxima b started with a deep global ocean, atmospheric loss would need to be extreme to eliminate surface liquid water entirely. In such a case, even a thinner remaining atmosphere might be sufficient to support liquid water under certain conditions. Temperature estimates for Proxima b vary widely depending on assumptions. Without an atmosphere, surface temperatures would be harsh and uneven. With an atmosphere, average temperatures could be moderate. Cloud cover could reflect excess radiation on the day side, stabilizing climate. Ocean circulation could transport heat efficiently. All of these possibilities stem from the star's small size and close habitable zone. Proxima b's challenges are direct consequences of Proxima Centauri's mass, radius, and energy output. The star does not provide a gentle, wide habitable zone. It provides a narrow, intense one that demands resilience. Beyond Proxima b, there is growing evidence that the system may contain additional planets. Some signals hint at a second, more distant planet, though its existence is not yet confirmed. If present, such a planet could influence Proxima b's orbit, potentially maintaining slight eccentricity and ongoing tidal heating. That heating could provide an additional energy source, warming the planet from within. This possibility broadens the concept of nearby worlds. Proxima b may not exist in isolation. it may be part of a compact planetary system shaped by the same processes that form many red dwarf systems. Multiple planets in close orbits could interact gravitationally, creating complex orbital dynamics. These interactions matter because they affect climate stability. Slight variations in orbit can change how energy is distributed over time. On Earth, orbital cycles influence ice ages. On Proxima b, even small changes could have outsized effect due to proximity to the star. The question of nearby worlds also extends beyond Proxima itself. Alpha Centauri A and B, the brighter companions in the system, may host planets as well. If confirmed, this would mean that our nearest stellar neighbourhood contains multiple planetary systems around very different types of stars. That diversity would offer an unprecedented opportunity for comparative study. Imagine 3 stars bound together by gravity, each with its own planets, each shaped by different stellar properties. Such a configuration would allow astronomers to examine how star type influences planetary formation and evolution within a single local environment. Proxima b's discovery has already influenced mission planning. Concepts for interstellar probes, such as light-sail spacecraft propelled by powerful lasers, often target Proxima because it is the closest system with a known, potentially rocky planet. These ideas remain speculative, but they reflect the planet's symbolic importance. Proxima b has become a focal point for discussions about the future of exploration, not because it is easy to reach, but because it is the least unreachable. Its distance of just over 4 light-years places it at the edge of what future technologies might plausibly attempt. There is also a philosophical aspect to the question of nearby worlds. For centuries, the nearest stars were abstract points of light. They had no known planets, no known structure beyond themselves. Proxima b changed that. It made the nearest star system feel less empty, more complex. This shift affects how we think about the galaxy. If the nearest star hosts a rocky planet in its habitable zone, what does that imply about more distant systems? Is this common or rare? Does proximity bias our discoveries, or does it reveal an underlying abundance? Statistical surveys suggest that Earth-sized planets around red dwarfs are common. Proxima b may not be unusual at all. It may simply be the first one close enough for us to notice. If so, the galaxy may be filled with nearby worlds orbiting small stars, each with its own version of the challenges Proxima b faces. The term nearby itself becomes relative here. 4 light-years is unimaginably far in human terms, yet cosmically close. Proxima b exists at the boundary between accessibility and remoteness. It is close enough to matter emotionally, far enough to remain mysterious. That tension drives much of the interest in the system. Proxima b is not a destination. It is a reference point, a reminder that planets exist not just around distant stars catalogued by number, but around the very stars that share our local region of the galaxy. Importantly, Proxima b also forces scientists to refine what they mean by habitability. Traditional models were built around sun-like stars. Proxima b does not fit those assumptions neatly. Its existence challenges simplistic criteria and encourages more flexible thinking. Habitability may not require Earth-like conditions. It may require adaptability. Proxima b, if it supports any form of life, would do so under conditions shaped by a small active star. That life, if it exists, would not resemble Earth's in detail. It would be adapted to red light, flare cycles, and tidal locking. This realization broadens the scope of astrobiology. It suggests that life may be possible in environments once dismissed as marginal. It also suggests that the most common habitats in the universe may look very different from Earth. The question of nearby worlds, then, is not just about Proxima b, it is about reframing expectations. It is about learning to recognize habitability in unfamiliar forms. Proxima b is valuable because it forces that recognition. Observational efforts continue. Astronomers monitor Proxima's flares to understand their frequency and intensity. They search for transits that could reveal Proxima B's radius. They model atmospheric escape and climate dynamics. Each study adds detail without resolving everything. This slow accumulation of knowledge mirrors the star's own slow life. There is no rush to answers. There is patience, iteration, and refinement. Proxima b remains a question rather than a conclusion. As we sit with that uncertainty, another layer begins to emerge. Proximity does not only affect observation and exploration, it affects how we think about distance itself. How close is close in the universe? How do we contextualize 4 light-years when dealing with objects that are small, dim, and yet profoundly influential? Closeness is one of those words that feels straightforward until you try to apply it beyond everyday life. We know what it means for a store to be close, or a neighbour to live nearby. These ideas are anchored in walking distance, driving time, or familiar landmarks. Once we move into space, especially into the realm of stars, that intuition stops being useful almost immediately. And yet, when Proxima Centauri is described as close, the word is not being used casually. It carries a very specific meaning that only becomes clear when we take the time to place it within the true scale of the cosmos. Proxima Centauri is just over 4 light-years away from Earth. That number appears often, repeated so frequently that it risks losing its weight. A light-year is not a unit of time, but of distance. The distance light travels in 1 year while moving at about 300,000 kilometers per second. Even stated plainly, that speed is difficult to grasp. Light circles Earth more than 7 times in a single second. In 1 year, it covers nearly 10 trillion kilometers. Multiply that by 4, and the result is a distance so large that it stops functioning as a practical number. So how can something 4 light-years away be considered close at all? The answer lies in comparison, not to human travel, but to the structure of our galaxy. The Milky Way is roughly 100,000 light-years across. Our Sun sits in one of its spiral arms, about 27,000 light-years from the galactic centre. Stars are scattered throughout this vast disk, separated by distances that often range from tens to hundreds of light-years. Many of the stars visible to the naked eye are dozens, hundreds, or even thousands of light-years away. Against that backdrop, 4 light-years is a tiny gap. If you imagine the Milky Way reduced to the size of a large country, the distance between the Sun and Proxima Centauri would shrink to something like the distance between neighbouring houses on the same street. They are not touching, but they are clearly part of the same local environment. They share the same region of the galaxy, the same general motion around the galactic centre, and a similar history shaped by the same large-scale events. This local environment is sometimes referred to as the solar neighbourhood. It is not a sharply defined region, but a loose collection of nearby stars moving through space together. Proxima Centauri is part of that neighbourhood. So are Alpha Centauri A and B, Barnard's star, and a handful of other nearby systems. These stars are close enough that their positions and motions can be measured with high precision, and their light arrives at Earth relatively unaltered by interstellar dust. Closeness, in this sense, is about belonging to the same local patch of the galaxy. Another way to understand this is to consider stellar density. On average, stars in the Milky Way are separated by several light-years. The exact spacing varies depending on location, but a distance of 4 or 5 light-years between stars is not unusual. Proxima Centauri is not unusually close because it is somehow drifting toward us. It is close because this is simply how stars are spaced. That fact alone reframes the meaning of proximity. The Sun is not isolated in a vast empty void. It exists in a region where stars are spaced a few light-years apart, each following its own orbit around the galactic centre. Proxima Centauri happens to be the one that currently sits nearest to us within that arrangement. This currently matters. Stars move. Over millions of years, distances change. Proxima Centauri will not always be the nearest star. In the distant past, another star may have held that title. In the distant future, another will take its place. Stellar neighborhoods are dynamic, slowly shifting as stars orbit the galaxy and pass one another. Even so, Proxima's closeness is not fleeting on human timescales. Its relative distance to the Sun changes only very gradually. For all practical purposes, it has been our nearest neighbour for tens of thousands of years, and will remain so for many thousands more. Closeness also matters because it affects how well we can observe something. Light spreads out as it travels. The farther a star is, the fainter it appears, and the more its light is affected by dust and gas along the way. Proxima's proximity means its light reaches us with minimal interference. Its faintness is intrinsic, not the result of distance. This is an important distinction. Many stars appear faint because they are far away. Proxima appears faint because it is small and cool. If it were placed at the same distance as some of the bright stars visible in the night sky, it would vanish entirely from view. The fact that we can detect it at all is because it is so close. That closeness allows astronomers to measure Proxima's properties with greater accuracy than they can for most stars. Distance uncertainties are smaller. Motions across the sky are easier to detect. Subtle changes in brightness or spectrum stand out more clearly. Proxima is not just close in a poetic sense. It is close in a way that improves the quality of scientific knowledge. There is also a geometric aspect to proximity that often goes unnoticed. Because Proxima is nearby, its apparent motion across the sky is relatively large. Over the course of a year, it traces a noticeable parallax shift as Earth orbits the Sun. Over decades, its proper motion carries it visibly across the background of more distant stars. These motions are signatures of closeness. Distant stars barely move at all from our perspective. Watching Proxima move through the sky over time reinforces the idea that it is part of our local environment, not a fixed remote object. It has a trajectory, it has a velocity, it shares space with us in a meaningful way. Yet even at this close distance, Proxima Centauri remains utterly unreachable with current technology. The fastest spacecraft humanity has ever launched would take tens of thousands of years to reach it. This is where the tension between cosmic closeness and human limitation becomes clear. 4 light-years is close in galactic terms, but it is still vast beyond any practical journey we can currently imagine. This duality is important. Proxima Centauri sits at the boundary between familiarity and remoteness. It is close enough to study in detail, but far enough to remain physically inaccessible. That boundary shapes much of the fascination surrounding it. The idea of interstellar travel often centers on Proxima precisely because it is the nearest option. If we cannot reach Proxima, reaching any star becomes vastly more difficult. It represents a minimum challenge rather than an easy one. In that sense, Proxima defines the scale of interstellar space for us. But closeness is not only about distance through space, it is also about time. The light we see from Proxima left the star just over 4 years ago. That means when we observe it, we're seeing it as it was 4 years in the past. In cosmic terms, this is almost immediate. For many stars, we see light that has been travelling for hundreds or thousands of years. Some objects are observed as they were millions of years ago. Seeing Proxima nearly in real time makes it feel more present. Changes we observe reflect relatively recent events. A flare detected today occurred just a few years ago, not in some distant epoch. This temporal closeness adds to the sense that Proxima is part of our current cosmic moment. It also means that if something significant were to change about Proxima Centauri, astronomers would know relatively quickly. A major change in brightness, motion, or activity would be detected within years rather than centuries. That immediacy is rare in astronomy. Closeness also affects how we think about cosmic isolation. For much of history, the nearest stars were assumed to be distant suns with no particular relevance to Earth, beyond navigation and curiosity. The discovery of Proxima b changed that. Suddenly the nearest star was not just a point of light, it was a system with at least one rocky planet in a region where liquid water might exist. That discovery made the universe feel less empty at close range. It suggested that planetary systems are not rare, even nearby. It also suggested that the conditions for rocky planets may arise naturally around many types of stars, including small, faint ones. In that sense, Proxima's closeness challenges the idea that Earth exists in a uniquely special neighbourhood. Our local region of the galaxy may be just as complex and populated as more distant regions. We simply notice it less because most nearby stars are faint. Another way to frame Proxima's proximity is to think in terms of cosmic maps. On a map of the galaxy, the Sun and Proxima Centauri would appear almost on top of each other. On a map of the local spiral arm, they would be separated by a barely visible gap. Only when zooming in to the scale of individual star systems does the distance become noticeable. This scaling problem is one of the reasons cosmic distances are so difficult to internalize. At one scale, everything seems close. At another, everything is impossibly far. Both views are correct, depending on context. Proxima's closeness also allows astronomers to test ideas about stellar populations. Because it is nearby, it can be studied in detail and used as a reference for understanding distant red dwarfs. Observations of Proxima inform models that are then applied to stars much farther away. In this way, Proxima acts as a local stand-in for a vast population. That representative role amplifies the importance of its proximity. A distant red dwarf might tell us something interesting, but Proxima tells us something reliable. Its data are cleaner, its uncertainties smaller, its measurements more constrained. The star's location relative to the Sun also has subtle gravitational implications. Although Proxima is bound to the Alpha Centauri system rather than directly to the Sun, the entire local neighbourhood moves through the galaxy together. Over long timescales, close stellar passages can perturb distant objects like comets in the Oort cloud. While Proxima's influence on the solar system is minimal, its existence reminds us that stellar neighbourhoods are not isolated bubbles. They interact gently over immense spans of time. There is also a psychological element to closeness. Knowing that the nearest star hosts a potentially rocky planet changes how people think about the universe. It shifts abstract curiosity into something more personal. The cosmos feels less like a distant backdrop and more like a surrounding environment with nearby points of interest. This feeling does not require travel. It arises from awareness. Proxima Centauri is close enough to matter conceptually. It occupies a place in our mental map of space that few other stars do. As technology advances, that closeness may become even more significant. Future telescopes may be able to image Proxima b directly. Spectroscopy might reveal atmospheric components. Each advancement leverages proximity. A similar planet around a star 50 light-years away would be far more difficult to study. So when we say Proxima Centauri is close in cosmic terms, we are not exaggerating. It is close relative to the size of the galaxy, close relative to typical stellar separations, close enough to study in detail, close enough to feel relevant. At the same time, it remains distant beyond any current means of physical exploration. That tension keeps it suspended between the familiar and the unreachable. Perspective is often shaped by whatever happens to be closest, and Proxima Centauri quietly exploits that fact. Because it sits so near to us in cosmic terms, it becomes more than just another star. It becomes a reference point, a corrective lens through which broader truths about the universe come into sharper focus. By studying Proxima carefully, astronomers have learned not only about one small red dwarf, but about how stars form, how common certain environments are, and how misleading human-centered assumptions can be when applied to a universe built on very different scales. One of the first lessons Proxima Centauri teaches is statistical rather than dramatic. The universe is not dominated by large, bright, sun-like stars. Those stars stand out visually, so they dominate our night sky and our cultural imagination, but they are not representative. Proxima Centauri belongs to the most common class of stars in the galaxy. Red dwarfs vastly outnumber all other stellar types combined. When you look at Proxima, you're not looking at an oddity, you're looking at the rule. This realization alone reshapes how astronomers think about the Milky Way. If most stars are small, cool, and long-lived, then most planetary systems form under conditions very different from those in our own solar system. The Sun stops being a universal template and becomes one example among many. Proxima Centauri, by contrast, becomes a guide to what typical might actually mean. Another lesson emerges from Proxima's size and longevity. The universe favours endurance over brilliance. Massive stars burn hot and fast, enriching space with heavy elements when they die, but their lives are short. Smaller stars like Proxima burn slowly and persist for immense spans of time. Over the full lifespan of the universe, it is the small stars that dominate the light budget, simply because they are still around when larger stars are long gone. This shifts how we think about cosmic history. Early in the universe, massive stars played an outsized role. They formed quickly, lived briefly, and seeded space with the elements needed for planets and life. But as time stretches forward, the balance changes. The future of the universe belongs to stars like Proxima, quiet, steady, and numerous. Studying Proxima offers a glimpse into that long future, not just into our present. Proxima Centauri also teaches us something subtle about efficiency. Its small mass and slow fusion rate mean it extracts far more usable time from its fuel than the Sun ever will. In energy terms, it is not powerful, but in temporal terms, it is extraordinarily productive. This efficiency challenges the assumption that higher output is always better or more significant. In stellar terms, restraint leads to longevity. That lesson echoes across astrophysics. Systems that release energy slowly often persist longer. Systems that release it quickly tend to burn out. Proxima Centauri embodies this principle in a form that is easy to study and quantify. There is also an important lesson about scale and relativity. Proxima is small compared to the Sun, but enormous compared to planets. It is faint compared to bright stars, but significant compared to most objects in the galaxy. It is close in cosmic terms, but unreachable in human ones. Each description is true within its context. None is complete on its own. This layered truth teaches caution. It reminds us that statements about the universe require context to be meaningful. Without context, words like small, close, or dim become misleading. Proxima Centauri forces astronomers to be precise, to specify reference points, and to resist intuitive shortcuts. Another lesson arises from how Proxima behaves. Its frequent flares challenge the idea that stability must be smooth. Proxima is stable over trillions of years, yet volatile on short timescales. The universe, it turns out, is full of systems that are stable in the long run but turbulent in the short term. Galaxies evolve slowly but undergo sudden mergers. Planets maintain long-term climates punctuated by abrupt changes. Stars shine steadily while producing flares. Proxima Centauri makes this pattern visible in a nearby, measurable way. It shows that variability does not imply fragility. A system can absorb disturbances and continue unchanged. This insight has implications far beyond stellar physics. It influences how scientists think about planetary climates, ecosystems, and even the long-term behavior of complex systems. Proxima also teaches humility about observation. For centuries, the nearest star system was assumed to consist only of Alpha Centauri A and B. Proxima was missed because it was faint. Its discovery required careful measurement, patience, and the willingness to look beyond what was obvious. This serves as a reminder that the universe is not obligated to reveal its most important features in the most visible way. Even today, Proxima continues to challenge observation. Its flares complicate measurements. Its faintness demands sensitive instruments. Its planets reveal themselves only indirectly. Knowledge accumulates slowly. not because the star is secretive, but because understanding requires persistence. This leads to another broader lesson. Astronomy advances not through single dramatic observations, but through sustained attention. Proxima Centauri has been observed for over a century, and each generation of instruments has added clarity, distance measurements improved, mass estimates refined, activity cycles catalogued, planetary signals teased out of noise. The picture sharpened gradually. That process mirrors the way science as a whole operates. Proxima Centauri becomes a case study in how understanding deepens over time. There is no final snapshot. There is only an evolving model that becomes more accurate as data accumulate. Proxima also reframes ideas about habitability. For a long time, discussions of life elsewhere were anchored to sun-like stars. Proxima b forces a reconsideration. If life can exist around red dwarfs, then the most common stars in the galaxy may host the most common habitats. This possibility expands the scope of astrobiology dramatically. Even if Proxima b itself is barren, its existence proves that rocky planets can form and persist in close orbits around small stars. That alone broadens the range of environments worth considering. The universe may be hospitable in ways that do not resemble Earth-specific circumstances. This realization pushes against anthropocentrism. Life elsewhere, if it exists, may not evolve under a yellow sun with a 24-hour day and moderate seasons. It may evolve under red light, tidal locking, and frequent flares. Proxima Centauri teaches that Earth conditions are not a universal standard. There is also a lesson about proximity and relevance. Proxima is important partly because it is close enough to study well. Many more distant red dwarfs may behave similarly, but Proxima allows theories to be tested rather than merely proposed. It bridges the gap between abstract models and concrete data. This proximity-driven importance highlights a broader truth. In science, what is nearest often becomes most influential, not because it is unique, but because it is accessible. Proxima Centauri reminds us that knowledge grows outward from what we can study most clearly. Another insight comes from how Proxima fits into its stellar system. It is bound to Alpha Centauri A and B, yet it is very different from them. 3 stars formed from the same molecular cloud, yet they followed divergent paths. 2 became sun-like stars. 1 became a red dwarf. This diversity within a single system illustrates how small differences in initial conditions can lead to very different outcomes. That lesson scales up. Galaxies, star clusters, and planetary systems all display diversity arising from shared origins. Proxima Centauri shows this at a scale we can observe in detail. The star also teaches us about patience in the universe. Its life unfolds so slowly that urgency becomes meaningless. There is no rush toward transformation, no dramatic endpoint on any timescale we care about. This challenges narratives that focus on explosive events as the primary drivers of cosmic change. Much of the universe evolves quietly. Proxima's steady presence over trillions of years suggests that the universe is not just a place of dramatic beginnings and endings, but of long, sustained middles. Most of cosmic history happens in these extended, uneventful phases. Proxima Centauri embodies that reality. There is an emotional lesson here as well, though it arises naturally from the science rather than from metaphor. Human lives are short, human projects are brief. Proxima's timescale dwarfs both. Studying such an object encourages a kind of temporal humility. It reminds us that our sense of importance is tied to perspective, not to absolute duration. Yet this humility does not diminish meaning. Instead, it reframes it. Our brief existence unfolds within a much larger, longer story. Proxima Centauri is part of that story, not as a protagonist, but as a persistent background presence that makes other events possible. Proxima also teaches restraint in conclusions. Despite decades of study, many questions remain unanswered. The true nature of Proxima b's atmosphere is unknown. The full architecture of the system is not yet clear. The long-term effects of flares on nearby planets are still being modelled. Each answer opens new questions. This open-endedness is not a failure. It is a feature of good science. Proxima Centauri remains interesting precisely because it has not been exhausted as a subject. It continues to generate hypotheses, experiments, and observations. Finally, Proxima Centauri teaches us that the universe does not scale itself to human expectations. It is not optimized for visibility, comfort, or narrative simplicity. It is shaped by physics, probability, and time. Small stars dominate. Quiet processes persist. Nearby objects can be faint. Important systems can be subtle. Learning these lessons requires letting go of assumptions and allowing evidence to guide interpretation. Proxima Centauri, by being small, close, long-lived, and active in unexpected ways, gently but persistently pushes us in that direction. After spending so much time stretched across stellar distances and unfamiliar timescales, it becomes almost necessary to come back slowly, not abruptly, not with a sharp conclusion, but by easing attention back toward the place where all of these questions began. Proxima Centauri does not demand a dramatic ending. It invites a gentle return, carrying what it has shown us without insisting that anything be wrapped up neatly. From Earth, Proxima Centauri remains invisible to the unaided eye. Even now, knowing what it is, how close it is, and how much attention it receives from astronomers, it does not reveal itself when you step outside at night. It does not compete with the moon, the planets, or the brighter stars. It stays hidden, quietly present whether we acknowledge it or not. That fact alone says something important. Significance in the universe is not always paired with visibility. The star that prompted questions about size, scale, longevity, and habitability continues shining without regard for whether anyone is paying attention. It does not grow brighter when discovered. It does not become more active because it hosts a planet of interest. Its fusion reactions proceed at the same slow pace they always have. The universe does not respond to curiosity. Curiosity responds to the universe. Returning to Earth with that in mind changes how familiar things feel. The Sun, for example, no longer appears as the default template for what a star should be. It becomes one variation among many, larger than most, brighter than most, shorter-lived than many. The Sun's warmth still matters in exactly the same way it did before, but its context has expanded. It is part of a broader population, not the centre of it. This shift in context is subtle, but it lingers. When you think about daylight, seasons, or the passage of years, those experiences remain unchanged. Yet somewhere in the background sits the awareness that stars like Proxima Centauri will continue long after the Sun has finished its main life. The present moment becomes a particular phase rather than a permanent condition. There is no need to treat that realization as heavy or unsettling. It can be held lightly. The universe has always operated on scales far larger than human ones. Learning about Proxima Centauri does not create that difference. It simply makes it visible. Back on Earth, size regains its familiar meanings. Rooms feel large or small again. Distances are measured in steps and minutes rather than light years. Time returns to calendars and clocks. And yet, the idea of scale does not completely disappear. It becomes layered. A mountain is still large, but it no longer feels absolute. A year is still meaningful, but it no longer feels like a universal unit. Proxima Centauri quietly encourages that layering. It does not erase human scale. It places it alongside others. One of the more grounding outcomes of this perspective is how it reframes urgency. Stars like Proxima remind us that not everything unfolds quickly, and not everything needs to. The star's long, steady life contrasts sharply with the pace of human concerns, deadlines, and anxieties. That contrast does not invalidate those concerns, but it can soften their edges. If a star can persist for trillions of years without rushing, then perhaps not every question requires immediate resolution. Perhaps not every uncertainty needs to be closed. Proxima's example is not instructional in a moral sense, but it is instructive in what it demonstrates physically. Stability does not require speed. Continuity does not require constant change. Standing on Earth, under a sky shaped by our own star, it becomes easier to appreciate how local our experience really is. The conditions that feel normal to us are the result of a specific stellar arrangement, a sun-like star, a certain distance, a certain mass, a certain lifespan. Proxima Centauri shows that there are many other ways for a star to exist, many other ways for planets to be arranged, many other environments where time unfolds differently. That realization expands possibility rather than limiting it. The universe does not funnel everything toward one outcome. It allows variation. Proxima Centauri is not an inferior version of the Sun. It is a different solution to the same physical constraints. Gravity, fusion, and energy balance operate everywhere, but the results vary. Even the idea of habitability, often framed in narrow terms, begins to loosen. Earth remains the only known example of life, and that fact still matters. But Proxima and its planet remind us that Earth's conditions are not the only conceivable ones. Life, if it exists elsewhere, may not mirror our expectations. It may arise under red light, persistent flares, and tidal locking. Or it may not arise at all. The point is not certainty, but openness. Proxima Centauri also invites a reconsideration of what near means in a personal sense. 4 light-years is far beyond reach, yet close enough to matter scientifically and conceptually. That duality reflects something familiar in everyday life as well. Some things feel distant because they are physically unreachable, yet they influence how we think and feel. Proxima occupies that category. It is not a destination, but it is a presence. That presence is quiet. There is no dramatic signal arriving from Proxima, no message encoded in its light. It does not ask to be interpreted, it simply exists, and through careful observation, it reveals patterns that are already there. The universe does not need to be dramatic to be informative. From Earth's surface, nights continue as they always have. The sky rotates, seasons change, human life unfolds at its usual pace. Nothing about Proxima Centauri alters those facts. What it alters is context. It widens the frame. In that widened frame, Earth feels neither insignificant nor central. It feels specific. One planet around one star, in one arrangement that happens to support life. Proxima Centauri becomes a reminder that specificity does not require uniqueness. There may be many specific arrangements, each with its own constraints and possibilities. There is also a quiet lesson in how much effort it takes to know even a nearby star. Proxima Centauri is the closest one beyond the Sun, yet understanding its size, mass, behaviour and planets has taken decades of observation and careful analysis. Knowledge does not arrive all at once. It accumulates through repeated attention. That process mirrors the way understanding develops in many areas of life. Clarity grows gradually. Assumptions are tested and refined. Proxima Centauri did not reveal its planet immediately. It did not reveal its full behaviour in a single observation. Each layer required time. Returning to Earth with that awareness can make uncertainty feel less like a problem and more like a natural state. The universe itself is not fully known, even at the smallest scales accessible to us. That incompleteness is not a failure. It is the condition under which exploration continues. There is something fitting about ending this long arc of attention with a star that is both small and enduring. Proxima Centauri does not overwhelm with brightness or size. It persists. It remains. It offers information to those willing to look carefully and patiently. Under our own star, that patience becomes easier to appreciate. The sun rises and sets with reliable regularity. Days pass, years accumulate. Against that steady backdrop, the idea of a star shining quietly for trillions of years does not feel alien. It feels like an extension of something already familiar, just stretched far beyond human limits. And so, without closing anything off, attention can rest here for a moment. On Earth, under a sun that feels warm and immediate, with the knowledge that nearby, in cosmic terms, another star continues its slow work, small, steady, and largely unseen. Proxima Centauri does not need to be watched constantly. It will still be there. Its light will still be travelling through space. Its planets will still be orbiting. The questions it raises will remain open, ready to be returned to whenever curiosity drifts outward again. For now, it is enough to let that star exist in the background of awareness, not as a destination or a conclusion, but as part of a larger ongoing structure that does not end here and does not require it to.